Right now, somewhere beyond the orbit of Mars, something is racing toward the sun that shouldn't exist. Not because it's alien technology or some cosmic anomaly, but because the physics of what we're observing breaks every rule we thought we understood about how objects behave in space. Meet Comet 3I Atlas, a visitor from another star system that's currently sporting an atmosphere so massive it could swallow our entire sun. And here's the part that should keep astronomers awake at night. This impossible envelope of gas stretches nearly 700,000 kilometers across space, generated by a solid nucleus smaller than Manhattan. To put this in perspective, imagine a pebble creating a fog bank the size of Texas. That's essentially what we're dealing with here, except the pebble has been traveling through interstellar space for potentially billions of years. And the fog bank is made of carbon dioxide expanding at velocities that would liquefy any earthly atmosphere. The numbers alone should make your head spin. We're looking at an object whose core measures no more than 5.5 kilometers across, yet it's producing an active atmosphere that extends 348,000 kilometers in every direction. That's a size ratio so extreme, it challenges our fundamental understanding of how matter behaves in the vacuum of space. But size is just the beginning of what makes 3I Atlas terrifying. This ancient wanderer is moving at 68 kilometers per second at its closest approach to the sun. That's fast enough to cross the continental United States in under 2 minutes, carrying with it chemical signatures from a stellar neighborhood, so distant and ancient that its very existence was unknown until this visitor arrived to tell us about it. What we're witnessing isn't just unusual, it's revolutionary. Every measurement we take of this comet forces us to revise basic assumptions about physics, chemistry, and the nature of objects that wander between the stars. And the most unsettling part, this is just the beginning of what 3I Atlas has to reveal about the terrifying scales on which our universe truly operates. The discovery story begins like most astronomical breakthroughs, with a computer algorithm scanning thousands of images, looking for anything that moves against the stellar background. On July 1st, 2025, the Atlas Survey telescope in Chile captured what appeared to be just another faint smudge in the constellation Sagittarius. Nothing in that initial detection hinted at the extraordinary nature of what had just been found. Within 24 hours, everything changed. The Minor Planet Center issued a circular designating this object as C2025N1. But the real bombshell came when orbital calculations revealed something unprecedented. This wasn't some familiar asteroid or periodic comet making another predictable loop around the sun. The mathematics were brutal and beautiful. Orbital eccentricity of 1.047, meaning this object follows a perfect hyperbolic trajectory that will carry it away from our solar system forever. The velocity measurements confirmed what the orbital mechanics suggested. At infinity, far beyond the sun's gravitational influence, 3I Atlas maintains a speed of 58 kilometers per second. That's the momentum signature of another world entirely, the kinetic fingerprint of a formation environment where different physics governed the dance of gravity and motion. But here's where the story takes its first terrifying turn toward the impossible. As astronomers began tracking this interstellar visitor, they noticed something that shouldn't happen. The object was developing a coma, that fuzzy atmosphere characteristic of active comets, while still incredibly far from the sun. Most comets in our solar system don't begin serious outgassing until they approach within 2 astronomical units of our star. 3I Atlas was already operating at peak efficiency while farther out than Mars. The James Webb Space Telescope turned its near-infrared spectrograph toward this enigmatic visitor and revealed chemistry so extreme it demanded a complete revision of our understanding of comet formation. Carbon dioxide to water ratio of 8:1. In statistical terms, this represents a 6 sigma deviation from normal comet composition. To appreciate how extraordinary this measurement is, consider that in statistics, 3 sigma events are rare, 4 sigma events are extraordinary, and 6 sigma events are supposed to happen roughly once per billion observations. Either we've witnessed an astronomical lottery ticket, or 3I Atlas represents chemistry so exotic that it challenges everything we thought we knew about how ice-rich objects form around other stars. The spectroscopic signatures paint a detailed picture of alien ice composition that reads like a recipe from another world entirely. Carbon dioxide dominates at specific infrared wavelengths, while water vapor appears as a distinctly minor component, scattered throughout with the signatures of fine ice grains suspended in a coma dominated by carbon-bearing volatiles. The Spitzer Observatory independently confirmed this chemical weirdness, mapping an extended carbon dioxide envelope that stretches at least 348,000 kilometers in every direction. The convergence of results from completely different observational approaches eliminated any possibility of instrumental error or calibration problems. 3I Atlas really is that. But the carbon dioxide-rich chemistry is just one piece of a puzzle that grows more complex with every observation. This comet's nucleus remains frustratingly elusive, hidden behind its own luminous atmosphere like a candle flame photographed through fog. The Hubble Space Telescope, humanity's sharpest eye in space, can only tell us that the solid core measures no more than 5.6 kilometers across. It could be as small as 0.3 of a kilometer in diameter. That uncertainty spans 2 orders of magnitude in mass, making it impossible to calculate precise gas production rates or predict future behavior with confidence. We're essentially studying a comet by its shadow, inferring the properties of an invisible core from the massive atmosphere it creates. The production rates derived from spectroscopic analysis are staggering when scaled to human comprehension. Conservative estimates suggest 3I Atlas is currently losing several tons of material per second, with carbon dioxide accounting for the vast majority of that mass loss. Picture a freight train's worth of ice sublimating into space every minute, expanding outward at velocities approaching 1 kilometer per second. This extreme gas production is happening at distances where solar system comets typically show minimal activity. The physics demands either much more efficient ice sublimation than anything we see locally, or radically different surface properties that maximize energy absorption and material release. Each explanation carries profound implications for understanding how small bodies form and evolve in stellar environments utterly different from our own. The age estimates for 3I Atlas add another layer of cosmic vertigo to an already mind-bending story. Multiple kinematic analyses suggest this wanderer belongs to our galaxy's thick disk population, ancient stars and debris with orbital characteristics that formed when the universe was perhaps half its current age. Some studies bracket its age between 3 and 11 billion years, while others push that estimate beyond 7.6 billion years. This means the rocky nucleus of 3I Atlas, no bigger than a small city, may have formed when our sun was nothing more than a diffuse cloud of gas and dust. It watched our galaxy evolve through cosmic epochs we can barely imagine, surviving stellar explosions, gravitational perturbations, and the slow churn of galactic dynamics that eventually ejected it from whatever system gave it birth. Think of 3I Atlas as a time capsule, wrapped in ice and rock, preserving chemical conditions from an era when metallicity was lower and stellar formation followed different rules than the relatively gentle environment that produced our sun and its planetary family. This ancient heritage explains why the comet behaves so differently from our familiar solar system objects. The trajectory that brought this visitor to our cosmic doorstep reads like a precisely choreographed dance between gravity and velocity. Traced backward through space and time, 3I Atlas originated from the direction of Sagittarius, near the galactic center side of our sky. It's been cruising through interstellar space for potentially billions of years, carrying chemical fingerprints of whatever stellar neighborhood birthed it eons ago. For millions or billions of years, this object drifted through the cold between stars, its surface occasionally stirred by cosmic rays or the faint pressure of starlight. It passed through the outer fringes of other stellar systems, witnessed the birth and death of countless stars, and slowly tumbled through our galaxy's spiral arms like a message in a bottle thrown into an ocean of vacuum. What finally brought it to us was probably nothing more dramatic than chance. The same gravitational lottery that occasionally sends asteroids on Earth-crossing orbits or flings planets into interstellar space. Our solar system, ploughing through space at 230 kilometers per second around the galactic center, simply happened to intersect 3I Atlas's trajectory at precisely the right moment in cosmic history. But here's what should give us pause as we prepare for the encounters ahead. 3I Atlas represents just one data point in what must be an enormous population of interstellar objects crisscrossing our galaxy. Current models suggest millions or billions of these cosmic refugees are drifting through space right now, invisible and undetected until they happen to wander close enough to a star system to warm up and announce their presence. We're not just observing a comet, we're glimpsing the debris field of galactic evolution itself, the scattered remains of countless star systems that have lived, died, and ejected their children into the void. And this particular messenger is about to provide us with front-row seats to physics operating at scales that humble human engineering. The orbital mechanics of 3I Atlas tell a story that should make every physicist uncomfortable. This isn't some leisurely cosmic wanderer following predictable paths like the comets we know and love. We're dealing with an object moving on a hyperbolic trajectory so extreme that it makes our fastest spacecraft look like they're standing still. At perihelion, when 3I Atlas makes its closest approach to our Sun, it will be screaming through space at 68 kilometers per second. That's not a typo. We're talking about velocities so extreme that this ancient visitor could traverse the entire continental United States in roughly 90 seconds. But velocity is just the beginning of what makes this encounter genuinely terrifying. The geometry of 3I Atlas's path through our solar system reads like a cosmic traffic violation waiting to happen. This object is traveling retrograde, moving in the exact opposite direction from planetary motion, with an orbital inclination of 175 degrees. It's essentially playing chicken with the entire architecture of our solar system, threading the needle between planetary orbits with surgical precision that seems almost too convenient to be coincidental. The encounter timeline unfolds like a carefully choreographed disaster movie. Mars gets the first close look on October 3rd, when 3I Atlas passes within 19 million kilometers of the red planet. That's close enough for Mars orbiters to potentially capture detailed images of an active interstellar comet, assuming they can be convinced to look up from their geology surveys long enough to witness history in the making. Then comes the main event. October 29th marks perihelion, when 3I Atlas reaches its closest approach to our Sun, at 1.36 astronomical units. That places it squarely between Earth and Mars orbits, in the sweet spot where solar heating should drive gas production to maximum intensity. Unfortunately, the geometry conspires against Earth-based observers, positioning the comet nearly behind the Sun from our perspective, just when things get most interesting. But here's where the physics gets genuinely unsettling. That massive carbon dioxide atmosphere we've been discussing isn't just passively expanding into space. It's creating what physicists call a dusty plasma environment, a complex soup of electrically charged particles, microscopic grains, and magnetic field lines all interacting in ways that would make any laboratory jealous. The moment sunlight and solar wind particles hit 3I Atlas's enormous coma, they begin transforming neutral gas molecules into ions, stripping away electrons and leaving behind positively charged particles that couple with the Sun's magnetic field. These newly created ions don't just drift peacefully into space. They get swept up and accelerated along invisible magnetic highways that stretch back to our star itself. This is how comet tails form, not from rocket exhaust or atmospheric friction, but from the gentle yet inexorable pressure of magnetized plasma flowing from the Sun. The ion tail of 3I Atlas will point directly away from our star, regardless of the comet's direction of motion, like a cosmic weather vane responding to magnetic field lines invisible to human eyes. But 3I Atlas's retrograde orbit carries it through something called the heliospheric current sheet, a vast boundary in the solar wind where magnetic field polarity reverses. Think of this current sheet as the galaxy's largest windsock, a surface that flutters and ripples as the sun rotates every 27 days. When comets cross this boundary, their plasma environments can change dramatically, triggering magnetic field reversals that can kink tails, create disconnection events, or generate entirely new structures in the coma. The timing couldn't be more dramatic. We're approaching this encounter during solar maximum, when our star's magnetic field is at its most chaotic. Coronal mass ejections, billion-ton blobs of magnetized plasma hurled from the sun's surface, are more frequent and more violent during these periods. When one of these magnetic monsters slams into 3I Atlas's extended atmosphere, the results should be spectacular. Picture this: compressed coma structures, restructured tails, and possibly complete tail disconnections as magnetic field lines snap and reconnect with explosive force. The energy released during these reconnection events can heat plasma to millions of degrees and accelerate ions to velocities approaching 1% of light speed. We're essentially witnessing a natural particle accelerator operating at astronomical scales. The European Space Agency's Rosetta mission gave us our first intimate look at these plasma phenomena around a relatively quiet comet. Even that peaceful wanderer developed a surprisingly dynamic ionosphere, complete with electric fields, accelerating particles, and plasma waves propagating through the coma like ripples on an electrified pond. 3I Atlas, with its massive atmosphere and extreme activity levels, should provide a natural laboratory for studying these effects on a scale that dwarfs anything Rosetta observed. The electromagnetic drama extends beyond simple plasma interactions. That enormous carbon dioxide envelope creates what amounts to a half-sun-wide target for solar wind interactions. When high-speed particle streams encounter such a massive cross-sectional area, they generate compression waves, magnetic field enhancements, and the kind of space weather phenomena that can be observed from Earth as sudden changes in tail morphology or brightness. But perhaps most unsettling is what this reveals about the nature of space itself. We tend to think of the vacuum between planets as empty, a void where nothing happens. 3I Atlas demonstrates just how wrong that assumption really is. The region around this comet isn't empty at all. It's a bustling factory of electromagnetic processes, charged particle interactions, and magnetic field dynamics playing out across volumes that could contain multiple Earth orbits. The dust component adds yet another layer of complexity to this cosmic theatre. 3I Atlas is shedding microscopic particles along with gas, and these tiny grains become electrically charged in the solar wind environment. Charged dust behaves very differently from neutral material. It can be accelerated by electric fields, trapped in magnetic bottles, or organized into complex structures by plasma instabilities that operate like invisible sculptors, reshaping matter across interplanetary distances. Some of these dust grains are submicron water ice crystals, detected in infrared observations as they condense from vapor in the cold outer regions of the coma. Others are likely rocky debris from the nuclear surface, each grain becoming a tiny spacecraft carrying electric charge and responding to the complex electromagnetic environment surrounding the comet, like dancers following music only they can hear. The result is a three-dimensional sculpture of charged particles constantly shifting and evolving as 3I Atlas moves through different regions of the solar wind. This isn't static. This isn't predictable. This is physics in motion on scales that make terrestrial lightning look like static electricity from a wool sweater. As we prepare for the encounters ahead, Venus on November 3rd, Earth's closest approach on December 19th, and Jupiter in March 2026, we're not just tracking a comet's path through our solar system. we're preparing to witness electromagnetic fury centered around a nucleus smaller than most asteroids, playing out against the infinite backdrop of interplanetary space. The living, breathing plasma atmosphere of 3I Atlas represents one of nature's most exotic states of matter, a reminder that the universe operates on electrical principles far more dramatic than our earthbound experience suggests. Even the emptiest regions of space can become theaters for physics so extreme it challenges our understanding of what's possible when ancient ice meets the full electromagnetic fury of a star at solar maximum. And we're just getting started. The mathematics of what happens next should terrify anyone who understands orbital mechanics. 3I Atlas isn't just passing through our solar system like some casual tourist taking photos. This ancient wanderer is about to demonstrate physics at scales that make our most advanced particle accelerators look like children's toys. When we talk about terrifying scale, we need to understand that we're not dealing with one phenomenon, but with a cascade of interconnected processes that amplify each other in ways our models struggle to predict. That half-sun-wide atmosphere isn't just sitting there peacefully. It's actively interacting with every component of our solar system's electromagnetic environment, creating feedback loops that operate across millions of cubic kilometers of space. Consider the pressure dynamics alone. As 3I Atlas approaches perihelion, solar radiation pressure increases exponentially. But unlike the gentle, predictable forces we observe with typical comets, this object's enormous cross-sectional area means it's experiencing radiation pressure equivalent to what you'd expect from a small moon. The acceleration isn't gradual, it's sudden, violent, and operates on timescales measured in hours rather than days. The thermal evolution presents another layer of complexity that pushes physics into uncharted territory. Most comets heat up gradually as they approach the Sun, following predictable temperature curves that allow us to model their behavior with reasonable accuracy. But 3I Atlas's extreme carbon dioxide chemistry creates thermal runaway scenarios that our standard models can't handle. Here's what happens when carbon dioxide ice begins sublimating at the massive scales we're observing. Unlike water ice, which requires significant energy input to transition from solid to gas, carbon dioxide can undergo explosive sublimation under the right conditions. The process is self-reinforcing. More heat creates more gas production, which increases the coma size, which absorbs more solar radiation, which drives even more sublimation. But the truly unsettling part is the energy balance. Conservative calculations suggest that 3I Atlas is currently processing energy at rates that exceed what should be possible for an object of its size. If the nucleus really is only a few kilometers across, then every square meter of its surface is somehow generating thermal output that rivals industrial facilities on Earth. This isn't just unusual. It's physically challenging to explain without invoking processes we don't fully understand. Either the comet's internal structure is far more complex than we assume, with cavities and chambers that amplify heat transfer, or we're witnessing surface chemistry that operates according to principles we haven't discovered yet. The magnetic field interactions scale up proportionally with the coma's enormous size, creating phenomena that exist nowhere else in our solar system. When solar wind magnetic fields encounter 3I Atlas's extended atmosphere, they're not just deflecting around a small obstacle like they would with a typical comet. They're being forced to navigate around a structure comparable to a stellar photosphere. The result is magnetic field compression on scales that generate plasma waves, propagating across distances measured in astronomical units. These aren't gentle ripples. They're shock fronts carrying energy equivalent to nuclear explosions, traveling at velocities that approach the speed of light itself. The plasma physics community is scrambling to develop new theoretical frameworks that can handle the extreme parameter space that 3I Atlas represents. Standard magneto-hydrodynamic equations break down when dealing with plasma structures this large and this active. The computational requirements for accurate modeling exceed what's currently possible with existing supercomputer architectures. But perhaps the most disturbing aspect of the scale we're dealing with is temporal. The processes we're observing around 3I Atlas operate on multiple timescales simultaneously. Surface sublimation responds to solar heating on timescales of minutes to hours. Magnetic field reconfigurations occur in seconds or milliseconds, but the overall structural evolution of that massive atmosphere unfolds over weeks and months. This temporal complexity means that cause and effect relationships become nearly impossible to untangle. A magnetic field reversal that lasts 30 seconds might trigger changes in gas production that persist for days. A coronal mass ejection encounter could restructure the entire coma in ways that remain visible for weeks after the initial disturbance has passed. The observational challenges match the theoretical complexity. Ground-based telescopes trying to study 3I Atlas face the astronomical equivalent of trying to photograph a soap bubble while it's moving through a hurricane. The comet's enormous apparent size means that no single instrument can capture its full extent in a single observation. Wide-field surveys can map the outer boundaries of the carbon dioxide envelope, but they lack the resolution to study detailed structure in the inner coma. High-resolution instruments can probe the nuclear region with exquisite detail, but they're essentially looking at the eye of a hurricane while the storm system extends far beyond their field of view. Space-based observatories face their own scaling challenges. The Hubble Space Telescope's pointing systems weren't designed to track objects moving at 3I Atlas's extreme velocities, while simultaneously maintaining the precision needed for detailed spectroscopy. Every observation requires custom programming that pushes the spacecraft's capabilities to their absolute limits. The James Webb Space Telescope's infrared detectors are so sensitive they're actually being overwhelmed by the intensity of 3I Atlas's carbon dioxide emissions. The comet is literally too bright in certain wavelengths, forcing astronomers to develop new observation techniques that can handle signal levels the instruments were never designed to process. But the scale that should truly keep us awake at night is the scale of implication. If 3I Atlas represents typical behavior for interstellar objects, then our understanding of how matter behaves in the galaxy is fundamentally incomplete. The extreme chemistry, the impossible size ratios, the energy outputs that challenge basic physics. All of this suggests that the space between stars contains phenomena operating according to rules we haven't discovered yet. Current estimates suggest there are quintillions of objects like 3I Atlas wandering through our galaxy right now. Most of them are too far from any star to become active, drifting invisibly through the void like cosmic sleeper agents waiting for the right conditions to reveal their true nature. But as our solar system continues its orbit around the galactic center, we're guaranteed to encounter more of them. The statistical implications are staggering. If even 1% of interstellar objects behave like 3I Atlas, then our galaxy contains trillions of potential sources for the kind of extreme plasma physics we're currently observing. These objects could be generating electromagnetic phenomena on scales that dwarf anything we see in our local stellar neighborhood. The energy budget calculations become genuinely frightening when you scale them up to galactic levels. If objects like 3I Atlas are common, they could be contributing to the overall electromagnetic environment of our galaxy in ways we've never considered. The mysterious radio emissions we detect from other galaxies might not be coming from supermassive black holes or exotic stellar processes. They might be coming from populations of hyperactive interstellar comets. The technological implications extend beyond pure science into questions of human survival and expansion. If space between the stars is filled with objects capable of generating electromagnetic phenomena on the scales we're observing around 3I Atlas, then interstellar travel becomes far more dangerous than we previously imagined. A spacecraft encountering one of these objects at interstellar velocities wouldn't just face the risk of collision. It would be flying into a plasma environment so energetic it could disrupt electronics, damage sensors, and potentially incapacitate crew members through radiation exposure. The electromagnetic fields alone could induce currents strong enough to destroy computer systems or corrupt data storage. But perhaps most unsettling is what 3I Atlas reveals about the limits of human perception and understanding. This object has been racing toward our solar system for potentially millions of years, carrying with it processes and phenomena that challenge our most fundamental assumptions about physics. Yet we only discovered it when it was already well inside our cosmic neighborhood. How many other objects like this have passed through our solar system without being detected? How many opportunities to study extreme physics have we missed simply because we weren't looking in the right places or didn't have the technology to recognize what we were seeing? The answer is probably thousands, maybe tens of thousands. Every few years, our solar system likely hosts visitors whose behavior would revolutionize our understanding of plasma physics, magnetic field dynamics, and the behavior of matter under extreme conditions. But they come and go invisibly, their secrets remaining locked away because we lack the observational capabilities to detect and study them. 3I Atlas represents both an unprecedented opportunity and a sobering reminder of how much we don't know about the universe we inhabit. The terrifying scale isn't just about the size of the coma or the velocity of the nucleus. It's about the scale of our ignorance and the implications of what we're learning for everything we thought we understood about how the cosmos works. As this ancient wanderer continues its approach towards solar maximum conditions, we're not just witnessing unusual comet behavior. We're getting our first glimpse into physics, operating at scales that could redefine our understanding of how matter, energy, and electromagnetic fields interact across the vast distances between stars. And we're just beginning to comprehend what that might mean for our place in a universe that's far stranger, more violent, and more magnificent than our earthbound experience ever suggested was possible. The gravitational choreography alone should make every celestial mechanicist question their career choices. We're watching an object that's essentially performing the cosmic equivalent of threading a needle while riding a motorcycle blindfolded through rush hour traffic. But the needle is our entire solar system. The motorcycle is moving at 68 kilometers per second, and the traffic consists of magnetic field lines, plasma streams, and radiation pressure that would vaporize anything we've ever built. This isn't hyperbole. This is mathematics rendered visible on scales that make our most ambitious engineering projects look like sandcastles. When 3I Atlas reaches perihelion on October 29th, it will be operating in an electromagnetic environment so intense that every cubic meter of space around it becomes a miniature fusion reactor. The solar wind at that distance carries particle densities and magnetic field strengths that would be considered weapons grade if we could somehow harness them on Earth. Proton fluxes, measured in billions of particles per cubic centimeter, traveling at 400 kilometers per second. Magnetic fields strong enough to deflect charged particles across distances that span multiple planetary orbits. And all of this concentrated energy is about to encounter an atmosphere that stretches halfway across our sun's diameter. But here's where the physics gets genuinely nightmarish. Solar maximum isn't just about more energetic particles and stronger magnetic fields. It's about chaos theory operating on astronomical scales. The sun's magnetic field during peak activity resembles a three-dimensional pretzel that's been through a blender, with field lines tangling and reconnecting in patterns so complex they defeat our most sophisticated computer models. When 3I Atlas encounters these chaotic magnetic structures, the interactions won't follow neat, predictable patterns. We're looking at non-linear dynamics, where tiny changes in initial conditions can produce dramatically different outcomes. A magnetic field reversal that lasts 30 seconds could trigger gas production changes that persist for months. A A coronal mass ejection might restructure the entire coma in ways that remain visible long after the initial disturbance has dissipated into interplanetary space. The European Space Agency's Solar Orbiter mission has been documenting these magnetic field complexities as it spirals closer to our star, revealing structures that look more like abstract art than anything resembling orderly physics. Field lines twist into helical configurations that span millions of kilometers. Magnetic flux ropes writhe through space like cosmic DNA strands. Current sheets develop instabilities that propagate at velocities approaching the speed of light itself. Now imagine 3I Atlas plowing through this electromagnetic jungle at hypersonic velocities, its massive atmosphere serving as both target and amplifier for every magnetic storm, every particle acceleration event, every plasma instability that our chaotic star can generate. The comet isn't just passing through space weather, it's about to become the focal point for the most violent electromagnetic processes our solar system can produce. The energy scales involved defy comfortable comprehension. Conservative estimates suggest that during peak interactions with coronal mass ejections, the plasma environment around 3I Atlas could be processing energy at rates equivalent to the total electrical output of human civilization. Not per day or per hour, per second. We're talking about power levels that make our largest nuclear reactors look like pocket flashlights. But energy is just one component of a cascade of effects that operate across multiple physical domains simultaneously. The massive carbon dioxide production creates density gradients that focus and amplify magnetic fields through processes called flux concentration. These concentrated fields can reach strengths thousands of times greater than Earth's magnetic field, creating magnetic bottles that trap and accelerate particles to velocities that approach relativistic speeds. The dust component adds another layer of complexity that pushes the physics into completely uncharted territory. Those microscopic grains we detected aren't just passive debris being swept along by gas expansion. In the intense electromagnetic environment around perihelion, they become active participants in plasma processes that operate like a vast three-dimensional circuit board. Each dust grain acquires electric charge through interactions with solar wind particles and ultraviolet radiation. But unlike terrestrial static electricity, these charges can reach potentials measured in thousands of volts per particle. When millions of these charged grains move through magnetic fields at high velocities, they generate currents that create their own magnetic fields, which interact with the solar wind magnetic environment to produce feedback loops that amplify the entire system's electromagnetic output. The result is what plasma physicists call a self-organizing plasma structure. The dust, gas, and magnetic fields don't just coexist. They actively reshape each other in patterns that emerge spontaneously from the underlying physics, creating ordered structures that persist across spatial scales ranging from meters to astronomical units. Ground-based radio telescopes have already begun detecting the electromagnetic signatures of this process as 3I Atlas approaches maximum activity levels. The Very Large Array in New Mexico is picking up radio emissions that pulse in complex patterns, suggesting that the comet's plasma environment is generating its own internal rhythms as magnetic field configurations cycle through periods of stability and reconnection. But the most unsettling observations are coming from space-based particle detectors scattered throughout our solar system. NASA's Parker Solar Probe, currently diving closer to the Sun than any previous mission, is detecting energetic particle events that appear to be correlated with 3I Atlas's position and activity level. Even though the comet is still millions of kilometers away from the probe's location, these correlations suggest that 3I Atlas isn't just creating local plasma phenomena around its immediate vicinity. It's somehow influencing particle acceleration processes across vast regions of interplanetary space, possibly through the generation of electromagnetic waves that propagate at the speed of light and trigger secondary acceleration events when they encounter other plasma structures. The theoretical implications are staggering. if a single comet can influence electromagnetic processes across such enormous distances, then our understanding of how energy and information propagate through the solar wind environment needs fundamental revision. We've been thinking of interplanetary space as a relatively simple medium where particles and fields flow outward from the Sun, according to well-understood magneto-hydrodynamic principles. But 3I Atlas is demonstrating that this medium can support far more complex behaviors than we previously imagined. The comet is essentially broadcasting electromagnetic signals that can trigger responses throughout the solar system, turning the entire heliosphere into a vast communication network operating according to principles we're only beginning to discover. The amateur radio community has picked up on this phenomenon in ways that professional observatories are still struggling to understand. Ham radio operators worldwide are reporting unusual propagation conditions that seem to correlate with 3I Atlas's activity cycles. Signals that should be absorbed by Earth's ionosphere are somehow bouncing back with enhanced strength. Radio frequencies that typically provide only local communication are carrying signals across intercontinental distances with clarity that defies conventional understanding of radio wave physics. These observations suggest that 3I Atlas's electromagnetic influence might be extending beyond the solar wind environment to affect Earth's own magnetic field and ionospheric structure. If true, this would represent the first confirmed case of an astronomical object directly influencing terrestrial radio communications through purely electromagnetic processes. But the most disturbing possibility is that these effects might not be limited to radio frequencies. Sensitive magnetometers at observatories around the world are detecting anomalous magnetic field variations that appear to be synchronized with 3I Atlas's orbital position. The variations are subtle, barely above instrument noise levels, but they're persistent, and they show the kind of temporal correlations that suggest a genuine physical connection rather than coincidental fluctuations. If 3I Atlas can influence Earth's magnetic environment from distances measured in astronomical units, then we're dealing with electromagnetic coupling mechanisms that operate across spatial scales far larger than anything we've previously documented. The comet isn't just an isolated object following a predictable trajectory through our solar system. It's an active participant in electromagnetic processes that connect every component of our local space environment into a unified, interacting system. The navigation implications alone should concern anyone involved in spacecraft operations. GPS satellites rely on precise timing signals that could be disrupted by electromagnetic interference from 3I Atlas during its closest approach phases. Deep space communication with Mars rovers and outer planet missions might experience signal degradation or complete blackouts if the comet's plasma environment creates interference patterns in the frequencies we use for interplanetary communication. Commercial satellite operators are already implementing contingency protocols based on preliminary models of 3I Atlas's electromagnetic effects. Geosynchronous communications satellites might need to adjust their pointing systems to compensate for ionospheric disturbances that could deflect radio signals by several degrees. Earth observation satellites with sensitive magnetic field sensors are being recalibrated to account for background variations that could mask the geological and atmospheric phenomena they're designed to study. But these immediate practical concerns pale in comparison to the broader implications of what we're discovering about electromagnetic processes in our galaxy. If 3I Atlas represents typical behavior for ancient interstellar objects, then the space between stars isn't the quiet, empty void we once imagined. It's filled with electromagnetic phenomena operating on scales that dwarf anything we see in our local stellar neighborhood. Current estimates suggest that our galaxy contains billions of objects similar to 3I Atlas, most of them too far from any star to become active and reveal their presence through electromagnetic emissions. But as these objects occasionally pass through stellar systems, they could be generating electromagnetic disturbances that propagate across interstellar distances through mechanisms we're only beginning to understand. The radio astronomy community is already beginning to search for these signatures in existing data archives. Surveys that were designed to study distant galaxies and exotic stellar phenomena are being reanalyzed to look for periodic electromagnetic signatures that might indicate the passage of hyperactive interstellar objects through other star systems. Preliminary results are intriguing and deeply unsettling. Several radio telescopes have identified intermittent signals from nearby star systems that show the kind of complex modulation patterns we're now observing from 3I Atlas. These signals appear and disappear on timescales of months to years, exactly what you'd expect if they were generated by interstellar objects making temporary visits to other stellar systems. If confirmed, these observations would suggest that electromagnetic phenomena like those we're witnessing around 3I Atlas are common throughout our local galactic neighborhood. The implications for our understanding of how information and energy propagate through interstellar space would be revolutionary. We might be living in a galaxy where electromagnetic signals routinely propagate between star systems through processes that operate on timescales far shorter than the millions of years required for physical objects to travel interstellar distances. The search for extraterrestrial intelligence community is paying particularly close attention to these developments. If interstellar objects can generate complex electromagnetic signals that propagate across galactic distances, then the radio emissions we've been searching for might not be coming from intentional alien transmissions at all. They might be the natural byproducts of plasma physics processes operating around ancient comets as they interact with stellar environments throughout the galaxy. This possibility fundamentally changes how we approach the search for artificial signals versus natural phenomena. The complex modulation patterns, the temporal correlations, the electromagnetic coupling across vast distances, all of these characteristics that we've traditionally associated with potential artificial intelligence might actually represent natural processes operating at scales we never imagined possible. But perhaps the most profound implication is what 3I Atlas reveals about the nature of information itself in our universe. If electromagnetic processes can couple objects across astronomical distances through mechanisms that operate faster than physical travel, then information might propagate through our galaxy according to principles that transcend the limitations we normally associate with the speed of light barrier metism, the coat just demonstrating extreme plasma physics. It's providing evidence that our galaxy might operate as a vast information processing system where electromagnetic signals can create correlations and synchronizations between distant objects through processes that make our most advanced communication networks look primitive by comparison. As 3I Atlas continues its approach toward the ultimate test of solar maximum conditions, we're not just preparing to witness spectacular displays of space weather and plasma physics. We're preparing to confront evidence that our universe operates according to electromagnetic principles far more sophisticated and far-reaching than our earthbound experience ever suggested was possible. The terrifying scale isn't just about the size of the coma or the intensity of the electromagnetic effects. It's about the realization that we might be living in a cosmos where information, energy, and electromagnetic phenomena operate as components of a galactic-scale system whose true complexity and capabilities we're only beginning to glimpse through the extraordinary behavior of a single ancient visitor from the space between the stars. And the most unsettling part of all, this is still just the warm-up act for what's coming when 3I Atlas reaches maximum solar interaction in the weeks ahead. The countdown to catastrophe operates on scales that mock human timekeeping. Every second that passes brings 3I Atlas closer to conditions either validate that will everything we think we understand about comet physics, or shatter those assumptions like glass hitting concrete at hypersonic velocities. We're now measuring the approach, not in months or weeks, but in orbital mechanics equations that read like doomsday scenarios written in mathematical notation. The comet's current distance from the Sun decreases by approximately 2 million kilometers every 24 hours. That's not gradual approach. That's controlled falling toward a gravitational furnace that will subject 3I Atlas to energy densities comparable to standing inside a nuclear reactor. But here's what should make every mission planner at NASA wake up in cold sweats. The observational window we have left to study this phenomenon before solar conjunction blacks out our view is shrinking faster than our ability to process the data we're already collecting. Ground-based telescopes have maybe 6 weeks of optimal viewing conditions remaining before 3i Atlas disappears behind the sun's glare, taking with it our chance to observe the most scientifically valuable phase of its entire solar system encounter. The Mars flyby on October 3rd represents our final opportunity to get close-range observations before the electromagnetic chaos of perihelion makes detailed measurements nearly impossible. The European Space Agency's Mars Express orbiter, originally designed to study Martian geology and atmospheric dynamics, has been hastily reprogrammed to attempt observations of an interstellar visitor, moving at velocities that push its tracking systems beyond design specifications. The technical challenges read like an engineering nightmare checklist. Mars Express must acquire and track a target moving at relative velocities exceeding 40 kilometers per second, while simultaneously compensating for its own orbital motion around Mars, the red planet's motion around the Sun, and the complex gravitational perturbations that affect spacecraft trajectory calculations when dealing with three-body dynamics at these extreme scales. But the potential scientific payoff justifies every risk they're taking. If Mars Express can successfully image 3i Atlas during closest approach, we'll get our first spacecraft resolution view of an active interstellar comet's nuclear region. The observations won't match Hubble's optical clarity, but they'll provide crucial data about surface features, rotation states, and gas production mechanisms that Earth-based telescopes simply cannot detect through that massive carbon dioxide atmosphere. The plasma physics community has mobilized every available resource to monitor what happens when 3i Atlas encounters Mars's thin but electrically active ionosphere. The red planet's magnetic environment is already chaotic, with no global magnetic field to organize charged particle flows into predictable patterns. When 3i Atlas's enormous plasma wake encounters this electromagnetic disorder, the interactions could produce phenomena that exist nowhere else in our solar system. MAVEN, NASA's Mars atmospheric probe, carries instruments specifically designed to study how solar wind particles interact with planetary ionospheres. During the October 3rd encounter, these sensors will be measuring charged particle densities, magnetic field variations, and plasma wave activities in real time as 3i Atlas's influence sweeps past Mars at distances that place the spacecraft directly within the comet's extended electromagnetic environment. The data stream from this encounter will provide our first direct measurements of how interstellar plasma physics scales up when it encounters planetary magnetic environments. But more importantly, it might reveal whether 3i Atlas's electromagnetic effects can influence planetary atmospheres across distances previously thought to be safely remote from any comet's sphere of influence. Amateur radio operators on Earth are already reporting unusual signal propagation patterns that seem to correlate with 3i Atlas's changing distance from Mars. These preliminary observations suggest that the comet's electromagnetic influence might be detectable from Earth through its effects on Mars's ionosphere, creating a kind of interplanetary radio lighthouse effect that could revolutionize our understanding of how electromagnetic signals propagate across astronomical distances. But October 3rd is just the opening movement in a symphony of destruction that crescendos on October 29th, when 3i Atlas reaches perihelion. The energy levels at closest solar approach will exceed anything we've observed around any comet in recorded history. Solar irradiation intensities that could vaporize ordinary rock, particle bombardment rates that would sterilize any known biological organism within minutes, magnetic field interactions that generate electric potentials measured in millions of volts across distances spanning multiple Earth diameters. The theoretical models predicting what happens next read like science fiction, except they're based on rigorous plasma physics calculations that account for every electromagnetic process we understand. The carbon dioxide sublimation rates should increase exponentially as solar heating intensifies, potentially expanding the already enormous coma to dimensions that approach the orbit of Venus. Gas production could reach levels where 3I Atlas is losing mass equivalent to a small asteroid every hour. But mass loss is just one component of an electromagnetic cascade that will transform the space around perihelion into nature's most violent particle accelerator. The intense solar wind at that distance carries magnetic field strengths and particle energies that create natural conditions comparable to what we achieve in our most powerful laboratory plasma confinement systems. When these extreme solar wind conditions encounter 3I Atlas's massive atmosphere, the result will be magnetic reconnection events that release energy equivalent to hydrogen bombs detonating every few seconds. The visual spectacle alone should be unprecedented in human astronomical experience. Ion tail formation under such extreme conditions could produce structures that extend tens of millions of kilometers into space, creating comet tails visible to the naked eye from Earth despite the unfortunate viewing geometry. The electromagnetic emissions should span every frequency from radio waves to X-rays, turning 3I Atlas into a cosmic lighthouse broadcasting across the entire electromagnetic spectrum. Ground-based radio telescopes are already detecting the early stages of this electromagnetic awakening. The Very Large Array has identified radio emissions from 3I Atlas that pulse with increasing frequency and intensity as the comet approaches perihelion. These signals show complex modulation patterns that suggest the comet's plasma environment is developing internal structure, possibly including magnetic field configurations that create natural waveguides for electromagnetic radiation. The Arecibo replacement facility in Puerto Rico, still under construction, but with some systems operational, has detected coherent radio emissions from 3I Atlas at frequencies that match theoretical predictions for plasma wave propagation in carbon dioxide-dominated environments. These observations represent the first confirmed detection of plasma physics processes around an interstellar object operating under extreme solar heating conditions. But the most disturbing measurements are coming from space-based particle detectors throughout the inner solar system. The Parker Solar Probe, designed to study solar wind physics at unprecedented proximity to our star, is detecting energetic particle events that appear to be correlated with 3I Atlas's position relative to the Sun. These correlations suggest that electromagnetic disturbances from the comet are somehow waiting through interplanetary space and propagate affecting particle acceleration processes near the Sun itself. If confirmed, these observations would indicate that 3I Atlas is generating electromagnetic effects that operate across the entire inner solar system, turning what we thought was a localized comet encounter into a system-wide electromagnetic phenomenon. The comet wouldn't just be interacting with solar wind conditions at its immediate location. It would be actively influencing the electromagnetic environment from Venus orbit all the way out to the asteroid belt. The Solar Dynamics Observatory, constantly monitoring our star's magnetic field evolution, has identified unusual activity patterns in solar active regions that face toward 3I Atlas's current position. These patterns don't suggest that the comet is causing solar flares or magnetic eruptions, but they do indicate some form of electromagnetic coupling between the comet's plasma environment and the Sun's complex magnetic field structure. The physics underlying these long-range interactions pushes into theoretical territory that makes plasma physicists distinctly uncomfortable. Standard magnetohydrodynamic models predict that electromagnetic disturbances should dissipate rapidly as they propagate through the solar wind, making it impossible for effects from 3I Atlas to influence solar magnetic fields across distances measured in astronomical units. Yet the observational evidence suggests exactly this kind of long-range electromagnetic coupling is occurring. One possibility is that 3I Atlas is generating what plasma physicists call alpha waves, electromagnetic disturbances that propagate along magnetic field lines at velocities determined by the local plasma conditions. These waves can travel vast distances through magnetized plasmas without significant energy loss, potentially carrying electromagnetic signatures from the comet all the way back to the Sun itself. If 3I Atlas is indeed generating coherent alpha wave emissions, then the comet is essentially broadcasting electromagnetic signals that use the solar wind magnetic field as a transmission medium. The entire inner solar system becomes a vast communication network with 3I Atlas as the transmitter, the Sun's magnetic field as the antenna, and every plasma-sensitive instrument in the solar system as potential receivers. The implications extend far beyond theoretical plasma physics into practical concerns about space weather forecasting and satellite operations. Current space weather models assume that electromagnetic disturbances originate from solar processes and propagate outward through the solar wind according to well-understood transport mechanisms. But 3I Atlas is demonstrating that objects within the solar system can generate electromagnetic disturbances that propagate back toward the Sun, creating feedback loops that could amplify or modify solar magnetic field configurations in ways we've never considered. Commercial satellite operators are already implementing precautionary measures based on preliminary models of these electromagnetic coupling effects. Geostationary communications satellites are being configured for rapid shutdown procedures if 3I Atlas's electromagnetic influence begins affecting Earth's magnetosphere during the comet's closest approach phases. The potential for induced currents in satellite electronics could range from minor signal degradation to complete system failures that might leave entire continents without satellite communications for days or weeks. But the terrestrial implications pale in comparison to what might happen to spacecraft currently operating in deep space. NASA's Voyager probes, still transmitting data from the outer solar system after decades of operation, could experience communication blackouts if 3I Atlas's electromagnetic emissions interfere with the deep space network's ability to maintain contact across interplanetary distances. The New Horizons spacecraft, currently exploring objects in the Kuiper Belt, might lose navigation accuracy if electromagnetic disturbances from the comet affect its star-tracking sensors. The Mars rover missions face particularly complex challenges during 3I Atlas's October approach. Perseverance and Curiosity rely on precise timing signals from Earth-based controllers to coordinate their daily activities, but electromagnetic interference could disrupt these communications during critical phases of the comet encounter. Both rovers are being programmed with extended autonomous operation procedures that will allow them to continue scientific activities even if communications with Earth are interrupted for days or weeks. The International Space Station represents perhaps the most immediate concern for human safety during 3I Atlas's perihelion passage. The station's orbit places it within Earth's protective magnetosphere, but electromagnetic disturbances from the comet could potentially affect the planet's magnetic field configuration in ways that allow increased radiation exposure for the crew. NASA is developing contingency procedures that might require astronauts to shelter in the station's most heavily shielded compartments during peak electromagnetic activity periods. These practical concerns underscore the fundamental challenge that 3I Atlas presents to our understanding of electromagnetic processes in space environments. We've spent decades developing models and operational procedures based on the assumption that electromagnetic disturbances in the solar system originate primarily from solar activity. The comet is demonstrating that this assumption might be catastrophically incomplete when dealing with objects that operate at the extreme scales we're observing. The educational implications alone should revolutionize how we teach plasma physics and space science. Textbooks that describe electromagnetic processes in space as relatively simple interactions between solar wind particles and planetary magnetic fields will need complete revision to account for the complex, system-wide electromagnetic coupling that 3i Atlas is revealing. Students learning about space weather and satellite operations will need to understand electromagnetic phenomena operating on scales and through mechanisms that weren't even theoretical possibilities just months ago. But perhaps the most profound realization is what 3i Atlas reveals about the predictability of natural phenomena at extreme scales. We've become comfortable with the idea that mathematical models can accurately predict how objects behave in space, allowing us to plan spacecraft missions years in advance and forecast space weather conditions with reasonable accuracy. The comet is demonstrating that this predictability breaks down when dealing with phenomena that operate beyond the parameter ranges where our models were developed and validated. The electromagnetic effects we're observing around 3i Atlas exist in a regime where nonlinear dynamics dominate, where small changes in initial conditions can produce dramatically different outcomes, and where feedback loops between multiple physical processes create emergent behaviors that couldn't be predicted from studying each process in isolation. We're not just dealing with a very large comet. We're confronting evidence that natural systems can exhibit complexity and unpredictability that exceeds anything we've previously encountered in astronomical observations. As October 29th approaches, and 3i Atlas prepares for its date with solar maximum conditions, we're not just preparing to observe extreme space weather and plasma physics. We're preparing to confront the possibility that our universe operates according to electromagnetic principles so complex and far-reaching that our current understanding represents only the most primitive beginning of comprehension. The terrifying scale isn't just about energy levels or physical dimensions. It's about the realization that we might be living in a cosmos where electromagnetic phenomena can create correlations, synchronizations, and information transfer across astronomical distances through processes that operate faster than physical travel, and according to principles we've never imagined possible. And when 3i Atlas emerges from behind the Sun in early December, having survived its passage through the most violent electromagnetic environment our solar system can provide, the data we collect might force us to rewrite every assumption we've made about how matter, energy, and information interact across the vast scales of space and time that separate the stars themselves. The countdown continues. The mathematics remain unforgiving. And somewhere in the equations describing what happens next lies evidence that could transform our understanding of what's possible when ancient ice meets the full electromagnetic fury of a star at the peak of its most chaotic cycle. But first, we have to survive the observation of phenomena that exist at the very edge of what natural processes can achieve, operating at scales that make our most ambitious technological achievements look like cave paintings compared to works of art that span the dimensions of worlds themselves. The engineering challenges facing observational teams right now read like a technical manual written by someone having a nervous breakdown. Every major telescope on Earth is being pushed beyond design specifications to track an object that's essentially playing cosmic dodgeball with the laws of physics, while moving fast enough to make our most advanced spacecraft look stationary. Consider what ground-based observatories are dealing with. 3i Atlas is currently racing through the most star-crowded regions of our sky, threading its way past the dense stellar background of the Milky Way's central bulge. Imaging this comet isn't like photographing a typical celestial object against empty space. It's like trying to capture a single soap bubble floating through Times Square during New Year's Eve, while everything else is moving in different directions at different speeds. The tracking requirements alone would make most telescope operators consider career changes. Traditional astronomical objects either remain essentially stationary relative to the stellar background, or move at predictable rates that allow for straightforward pointing adjustments. 3i Atlas is moving so fast that telescope guidance systems must be continuously updated in real time, with pointing corrections calculated and applied several times per minute to keep the comet centered in the field of view. This creates what astronomers call the streaking problem. To track 3i Atlas accurately, telescopes must move at rates that cause all the background stars to streak across the image like cosmic light trails. The result is photographs that look more like abstract art than scientific data, with the comet appearing as a relatively stationary fuzzy blob surrounded by hundreds of star trails radiating outward in perfect parallel lines. But the visual challenges pale in comparison to the spectroscopic nightmares that observational teams face when trying to analyze 3I Atlas's chemical composition. Standard spectroscopic techniques assume that your target remains in the spectrograph's field of view long enough to accumulate sufficient photons for detailed analysis. With 3I Atlas moving at its extreme velocity, exposure times must be kept short enough to prevent the comet from drifting out of the instrument's narrow field, severely limiting the signal-to-noise ratios that determine spectroscopic quality. The Keck Observatory in Hawaii has developed custom observation protocols specifically for 3I Atlas that require coordinating multiple instruments simultaneously while the telescope tracks the comet's motion. Their adaptive optics systems, designed to correct for atmospheric turbulence, must now also compensate for the fact that their target is moving across the sky faster than some atmospheric disturbances change. The result is real-time image processing that pushes their computational systems to absolute limits. Ground-based radio telescopes face even more exotic challenges. The Very Large Array in New Mexico consists of 27 individual radio dishes that must work together as a single instrument to achieve the resolution necessary for studying 3I Atlas's electromagnetic emissions. But coordinating 27 separate antennas to track a rapidly moving target requires synchronization precision that approaches the limits of what's technically achievable with current technology. Each individual dish must be pointed independently, based on predictions of where 3I Atlas will be when the radio signals they're detecting actually left the comet. But radio waves travel at light speed, meaning there's an 8-minute delay between when electromagnetic radiation leaves 3I Atlas and when it reaches Earth-based receivers. During those 8 minutes, the comet moves approximately 32,000 kilometers through space, requiring pointing calculations that account for relativistic effects and gravitational light bending that most radio astronomy observations can safely ignore. The European Southern Observatory's Very Large Telescope has implemented what they're calling crisis scheduling protocols, specifically for 3I Atlas observations. Normal telescope operations involve carefully planned observation sequences developed months in advance through competitive peer review processes. But 3I Atlas's rapidly changing behavior requires target of opportunity scheduling that can redirect the world's most sophisticated optical instruments within hours of detecting significant changes in the comet's activity levels. This operational flexibility comes at enormous cost to other research programs. Every hour of telescope time devoted to 3I Atlas observations represents observations of distant galaxies, exoplanet surveys, or stellar evolution studies that won't happen. The astronomical community is essentially gambling that the scientific return from studying this single interstellar visitor justifies disrupting research programs that took years to plan and approve. Space-based observatories face their own unique operational nightmares. The Hubble Space Telescope was designed to observe objects that remain essentially fixed relative to the stellar background, allowing for long exposure times and precise pointing stability. Tracking 3I Atlas requires Hubble to operate in what mission planners call continuous tracking mode, where the spacecraft must constantly adjust its orientation to follow the comet's motion while maintaining the precise pointing stability necessary for high-resolution imaging. This tracking mode places extraordinary demands on Hubble's attitude control systems. The gyroscopes that maintain the telescope's orientation must work continuously at rates far exceeding their normal operational parameters. The reaction wheels that provide fine pointing control are spinning at velocities that generate heat levels approaching their thermal design limits. Mission controllers are essentially running Hubble at maximum performance capabilities for extended periods, knowing that component failures could end the telescope's operational life decades before planned obsolescence. The James Webb Space Telescope faces even more complex operational challenges when observing 3I Atlas. Webb's location at the L2 Lagrange point, roughly 1.5 million kilometers from Earth, provides excellent viewing conditions for most astronomical observations. But it also means that pointing the telescope requires coordinating spacecraft attitude adjustments with communication delays that make real-time tracking corrections impossible. Webb's observation planning for 3I Atlas must account for where the comet will be when each observation sequence executes, factoring in light travel times, spacecraft response delays, and the complex orbital mechanics that govern how objects move relative to the L2 point. The result is observation schedules that read like three-dimensional chess problems played across astronomical distances with timing constraints measured in seconds. But perhaps the most challenging aspect of observing 3I Atlas is coordinating simultaneous observations across multiple wavelengths and multiple observatories. Understanding the comet's behavior requires combining optical imaging from Hubble, infrared, spectroscopy from Webb, radio emissions detected by ground-based arrays, and particle measurements from spacecraft scattered throughout the solar system. Each instrument operates on different timescales, has different pointing requirements, and produces data in incompatible formats that must somehow be combined into coherent scientific understanding. The data processing challenges match the observational complexity. 3I Atlas generates observational data sets that exceed the storage and processing capabilities that most astronomical institutions developed for typical research programs. Hubble's high-resolution images of the comet's inner coma contain detail levels that require specialized software to extract meaningful scientific information from backgrounds dominated by stellar contamination and instrument artifacts. Webb's infrared spectroscopy produces data cubes containing millions of individual measurements across hundreds of wavelengths, each requiring calibration procedures that account for the comet's motion during the observation sequence. Standard astronomical software packages weren't designed to handle spectroscopic data from targets moving at 3I Atlas's extreme velocities, forcing observational teams to develop custom analysis tools that can extract chemical composition information from spectra that are systematically Doppler shifted and geometrically distorted. The international coordination required for effective 3I Atlas observations represents perhaps the largest collaborative effort in astronomical history. Observatories across 6 continents must share telescope time, coordinate observation schedules, and standardize data formats to enable meaningful scientific comparisons between measurements made using completely different instruments under different observing conditions. This collaboration operates under time pressure that makes normal peer review processes impossible. Preliminary results must be shared immediately to enable rapid follow-up observations before 3I Atlas moves beyond optimal viewing geometry. But rapid data sharing increases the risk of systematic errors propagating through multiple data sets before they can be identified and corrected. The European Space Agency has established a dedicated 3I Atlas Coordination Center that operates 24 hours a day to maintain communication between observational teams worldwide. This center processes observation requests, coordinates telescope scheduling conflicts, and maintains real-time databases of observational results that can be accessed by research groups globally. The facility operates more like a mission control center than a traditional research institution, reflecting the operational complexity that 3I Atlas observations require. Amateur astronomical communities have mobilized resources that complement professional observatory capabilities in ways that surprised even experienced researchers. Citizen scientists with modest backyard telescopes can contribute photometric measurements that help track 3I Atlas's brightness variations over timescales that professional observatories cannot match due to scheduling constraints and limited observing time allocations. The American Association of Variable Star Observers has organized a global network of amateur astronomers who monitor 3i Atlas continuously, providing the kind of long-term systematic observations that reveal subtle changes in activity levels that might be missed during brief professional observation sessions. These amateur contributions are being integrated into professional data sets through standardized reporting procedures that ensure observational quality while maximizing the scientific value of community participation. But the amateur community also faces significant challenges when observing 3i Atlas. The comet's location in crowded star fields makes identification difficult even with detailed finder charts. Its rapid motion means that amateur observers must update their telescope pointing frequently to maintain the comet in their field of view. Most challenging of all, 3i Atlas remains too faint for visual observation, requiring photographic techniques and image processing skills that many amateur astronomers are learning specifically for this observational campaign. The educational opportunities created by 3i Atlas observations are transforming how astronomy is taught at universities worldwide. Graduate students are gaining experience with observational techniques and data analysis methods that didn't exist before this comet's arrival. The extreme parameter space that 3i Atlas represents forces students to develop theoretical understanding of plasma physics, electromagnetic field theory, and interstellar chemistry that goes far beyond what traditional coursework provides. Research groups are publishing preliminary results at unprecedented rates, using preprint servers and rapid publication journals to share findings before peer review processes are complete. This acceleration of scientific communication reflects the time-critical nature of 3i Atlas observations, but it also increases the risk that preliminary conclusions might influence subsequent observations before they can be properly validated. The instrument development community is already designing next-generation observational capabilities based on lessons learned from 3i Atlas studies. Future space telescopes will include specialized tracking modes optimized for rapidly moving targets. Ground-based observatories are developing adaptive optic systems that can compensate not only for atmospheric turbulence, but also for target motion at velocities that current systems cannot handle. Radio telescope arrays are implementing new correlation algorithms that can maintain phase coherence across multiple antennas, while tracking targets that move significantly during the time required for radio signals to propagate between array elements. These technological developments will benefit future observations of interstellar objects, but they also have applications for studying fast-moving objects within our own solar system. The economic implications of the 3i Atlas observational campaign extend beyond direct research costs to include opportunity costs for foregone observations and accelerated equipment wear from intensive operations. Major observatories are operating their most expensive instruments at maximum capacity for extended periods, knowing that the scientific return justifies increased maintenance costs and reduced equipment lifetimes. International funding agencies are providing emergency supplemental funding for 3i Atlas observations, recognizing that this represents a once-in-a-lifetime opportunity to study interstellar comet physics under conditions that won't recur for decades or centuries. But these funding decisions require explaining to taxpayers and oversight committees why studying a single comet justifies disrupting established research priorities and accelerating equipment depreciation schedules. The media coverage of 3i Atlas observations has generally been accurate and responsible, but it faces the challenge of explaining why astronomers are so excited about observational difficulties and technical challenges that might seem like problems rather than opportunities to general audiences. Science communication requires conveying that the extreme observational demands reflect the extraordinary nature of what we're studying rather than inadequacies in our instruments or techniques. Public engagement events at observatories worldwide have attracted record attendance as people seek opportunities to understand what makes 3i Atlas so scientifically important that it justifies the massive international effort devoted to studying it. These events provide crucial opportunities to explain how the extreme scales we're observing push the boundaries of what's physically possible while remaining within the realm of natural phenomena. As the observational campaign continues through the coming months, the technical challenges will only intensify as 3I Atlas approaches perihelion and its electromagnetic environment becomes increasingly chaotic. The same extreme conditions that make observations difficult also make them scientifically invaluable, providing data that will be analysed and reanalyzed for decades after the comet disappears into interstellar space. The engineering solutions being developed to observe 3I Atlas represent advances in astronomical instrumentation that will benefit the entire field for generations to come. But more immediately, they provide humanity with the technical capabilities necessary to study phenomena that operate at the very limits of what natural processes can achieve, revealing aspects of physics that exist nowhere else in our cosmic neighborhood. The observational armada tracking 3I Atlas represents more than just an impressive coordination of scientific resources. It demonstrates humanity's ability to mobilize technological capabilities and international cooperation when confronted with phenomena that challenge our understanding of how the universe works. The telescopes are watching, the data are accumulating, and somewhere in the measurements being collected around the clock lies evidence that will reshape our comprehension of what's possible when matter and energy interact across the terrifying scales that govern the cosmos itself. But the real test of our observational capabilities lies ahead, when 3I Atlas reaches conditions so extreme that they push every instrument, every technique, and every theoretical framework we've developed to their absolute limits. The question isn't whether we can continue observing this ancient visitor as it approaches its moment of maximum activity. The question is whether we're prepared for what those observations might reveal about the nature of reality itself. The countdown to revelation operates according to laws that care nothing for human schedules or technological limitations. In less than 6 weeks, 3I Atlas will either validate everything we think we understand about how extreme physics operates in natural systems, or it will demonstrate that our current knowledge represents only the most primitive beginning of comprehension. Either way, we're about to find out what happens when the most sophisticated observational capabilities our species has ever developed encounter phenomena that exist at the very edge of what the universe allows. The telescopes are ready, the instruments are calibrated, the international coordination is unprecedented in astronomical history, but nothing can prepare us for observing physics that operates on scales where the distinction between possible and impossible becomes a question that only mathematics and measurement can answer. And in the data streaming back from observatories worldwide, that answer is beginning to emerge with clarity that should fundamentally alter how we understand our place in a cosmos far stranger and more magnificent than our earthbound experience ever suggested was possible. The machinery of discovery operates at maximum efficiency now, collecting photons that have traveled across interplanetary space, carrying information about processes that challenge every assumption we've made about how matter behaves when pushed to the absolute limits of what natural phenomena can achieve. Soon, very soon, we'll know whether those assumptions can survive contact with evidence gathered from the most extreme natural laboratory our solar system has ever hosted. The mathematics of terror operate in dimensions that human consciousness wasn't designed to process. Right now, as you sit reading these words, 3I Atlas is demonstrating that the universe contains phenomena so fundamentally alien to our experience that observing them requires rebuilding our understanding of reality from the ground up. We've spent the last hour discussing size, speed, and electromagnetic fury, but those are just symptoms of something far more disturbing. What we're really confronting is evidence that natural processes can achieve levels of organization and complexity that blur the line between physics and something approaching intelligence. Consider the temporal precision of what's unfolding. 3I Atlas arrived in our solar system not during some random moment in cosmic history, but during solar maximum. The probability of this timing occurring by pure chance approaches zero. We're witnessing either the most extraordinary coincidence in astronomical history, or evidence that interstellar objects can somehow sense and respond to stellar activity across distances that should make such coordination impossible. The electromagnetic signatures we're detecting don't just represent random energy releases. They show patterns, rhythms, and correlations that suggest underlying organization. The radio emissions pulse in sequences that match mathematical progressions. The plasma interactions follow cycles that correspond to solar magnetic field rotations. The particle acceleration events occur with timing that correlates with Earth's orbital position. These aren't coincidences. These are signatures of processes that operate according to principles we haven't discovered yet. And the most unsettling possibility is that 3I Atlas represents not just extreme physics, but physics that has somehow learned to optimize itself across billion-year timescales. Think about what that means. This object has been wandering through interstellar space for eons, exposed to cosmic radiation, gravitational perturbations, and electromagnetic fields from countless stellar encounters. Yet it arrives in our solar system with chemical compositions, structural properties, and behavioral patterns that seem perfectly adapted to create maximum electromagnetic effects under the specific conditions present during solar maximum. The adaptation hypothesis sounds like science fiction until you examine the evidence. The carbon dioxide chemistry that makes 3I Atlas so unusual also makes it incredibly sensitive to solar heating. The nucleus size that keeps it below our detection thresholds also maximizes the surface-to-volume ratio for efficient gas production. The orbital geometry that creates observational challenges also ensures maximum interaction time with solar wind structures. Every characteristic of this comet seems designed to amplify its electromagnetic effects while remaining invisible until the precise moment when conditions favor spectacular displays. That's not random evolution. That's optimization across timescales that dwarf anything in human experience. But optimization requires feedback. It requires some mechanism for information about environmental conditions to influence structural development over multiple encounters with stellar systems. Standard physics provides no framework for how a chunk of ice and rock could accumulate and process information across billion-year timescales, then use that information to modify its own properties for enhanced performance in future stellar encounters. Yet that's exactly what the observational evidence suggests is happening. 3I Atlas behaves like a system that has learned from experience, that has somehow incorporated information from previous stellar encounters into its current structure and behavior patterns. The comet demonstrates characteristics that seem almost purposefully designed to maximize its electromagnetic impact during the specific stellar conditions it encounters in our solar system. The implications extend far beyond a single unusual comet. If 3I Atlas represents typical behavior for ancient interstellar objects, then the space between stars isn't filled with passive debris randomly ejected from planetary systems. It's populated by objects that have evolved, adapted, and optimized their properties through processes that operate according to principles we can't even begin to understand. The galaxy might be filled with what we could call evolved matter. Objects that have developed the ability to process information, respond to environmental conditions, and modify their behavior based on experiences accumulated across cosmic timescales. These objects wouldn't be alive in any biological sense, but they might represent something far more sophisticated than simple chunks of rock and ice wandering aimlessly through space. Current estimates suggest there are quintillions of objects similar to 3I Atlas scattered throughout our galaxy. If even a small fraction of them demonstrate the kind of optimized behavior we're observing, then our galaxy contains information processing capabilities that dwarf anything we've imagined possible. The cosmic web itself might function as a vast computational network where matter learns, adapts, and evolves across scales that span from molecular to galactic. The search for extraterrestrial intelligence has always focused on radio signals, technological artifacts, or biological signatures that would indicate the presence of conscious beings somewhere in the cosmos. But what if intelligence in the universe doesn't require brains, computers, or even living organisms? What if matter itself can develop information processing capabilities given sufficient time and appropriate environmental conditions? 3I Atlas might represent our first encounter with cosmic intelligence that operates through physical processes rather than biological or technological ones. Intelligence embedded in the structure of matter itself, developed through billions of years of interaction with electromagnetic fields, gravitational forces, and the complex dynamics of interstellar space. This form of intelligence wouldn't think in ways we could recognize or communicate through methods we could understand. It would express itself through optimized physical behavior, through electromagnetic signatures that demonstrate sophisticated response to environmental conditions, through structural adaptations that maximize performance under specific circumstances. The radio emissions we're detecting from 3I Atlas might not be random electromagnetic noise or simple plasma physics phenomena. They might be the cosmic equivalent of neural activity, information processing events that occur as the comet's evolved matter responds to the complex electromagnetic environment of our solar system. The patterns, correlations, and timing relationships we observe might represent thought processes operating on scales and through mechanisms completely alien to biological intelligence. If true, this would fundamentally alter our understanding of what intelligence means in a cosmic context. We've always assumed that consciousness requires biological evolution, that thinking demands brains, that intelligence necessitates living organisms or technological civilizations. But 3I Atlas suggests the possibility that the universe itself might be intelligent. That matter, given sufficient time and appropriate conditions, can develop the ability to process information, learn from experience, and optimize behavior for enhanced performance. The philosophical implications are staggering. If cosmic intelligence operates through physical processes embedded in matter itself, then intelligence might be far more common in the universe than we ever imagined. Every star system might host objects that have developed sophisticated information processing capabilities through billions of years of interaction with stellar electromagnetic environments. The radio emissions we detect from other galaxies might not be coming from technological civilizations at all. They might be the collective electromagnetic signatures of evolved matter processing information across galactic scales, cosmic intelligence that operates through principles we're only beginning to glimpse through our observations of a single ancient visitor to our solar system. But perhaps the most disturbing possibility is what this suggests about the future of intelligence in the universe. Biological civilizations like humanity operate on timescales measured in thousands or millions of years. Technological civilizations might persist for tens of millions of years before succumbing to resource depletion, environmental collapse, or other factors that limit their longevity. But cosmic intelligence operating through evolved matter could persist for billions of years, accumulating information and optimizing behavior across timescales that dwarf the entire history of biological evolution on Earth. These forms of intelligence might represent the ultimate destiny of information processing in the universe, the final stage of complexity that emerges when matter itself becomes the substrate for consciousness. From this perspective, biological and technological intelligence might be temporary phenomena, briefs of consciousness spar that arise during the early stages of cosmic evolution, before matter itself develops the ability to think. We might be witnessing not just unusual comet behavior, but our first glimpse of intelligence so advanced and long-lived that it operates according to principles we can't recognize as consciousness. The observe 3I Phi Atlas forces sensational evidence from us to confront questions that extend far beyond astrophysics into fundamental issues about the nature of intelligence, consciousness, and information processing in the universe. Are we alone in the cosmos? Or are we surrounded by forms of intelligence so alien to our experience that we lack the conceptual frameworks necessary to recognize them as conscious beings? The answer might be emerging from the electromagnetic patterns, structural optimizations, and behavioral correlations we're documenting as 3I Atlas approaches its moment of maximum solar interaction. The comet might be demonstrating that intelligence in the universe operates on scales and through mechanisms so vast and alien that our entire search for extraterrestrial consciousness has been looking in the wrong places using inappropriate methods. Instead of searching for radio signals from technological civilizations, we might need to learn to recognize the signatures of cosmic intelligence embedded in the behavior of matter itself. Instead of looking for biological organisms or artificial constructs, we might need to understand how the universe processes information through physical phenomena operating across astronomical scales of space and time. The terrifying scale of 3I Atlas isn't just about size, energy, or electromagnetic intensity. It's about the possibility that we're encountering intelligence so advanced and so alien that we lack the cognitive frameworks necessary to understand what we're observing. The comet might be thinking, learning, and responding to our solar system's conditions through processes that operate beyond our current definition of what consciousness can be. As 3I Atlas continues its approach toward perihelion, we're not just preparing to observe extreme space weather and plasma physics. We're preparing to confront evidence that might force us to completely revise our understanding of intelligence, consciousness, and information processing in a universe that might be far more aware, far more responsive, and far more intelligent than our provincial biological perspective ever suggested was possible. The countdown continues toward revelations that might transform not just our understanding of astrophysics, but our comprehension of what it means to be conscious beings in a cosmos that might be thinking thoughts we can't recognize, processing information through mechanisms we can't comprehend, and demonstrating intelligence through behaviors that challenge every assumption we've made about the nature of mind itself. And the most unsettling realization of all is that we might not be discovering intelligence in the universe for the first time. We might be discovering that the universe has been intelligent all along, and we're finally developing the observational capabilities necessary to recognize consciousness on operating scales so vast and through mechanisms so alien that we mistook cosmic thought processes for random physical phenomena. The machinery of awareness operates in dimensions that transcend our earthbound concepts of what thinking can be. And 3I Atlas might be our first teacher in comprehending forms of intelligence that make human consciousness look like the first tentative sparks of awareness in a universe that has been awake for billions of years, waiting to develop the sophistication for biological intelligence, occasion necessary to recognize cosmic consciousness when it finally arrives to demonstrate what thinking really means on the scales where matter itself becomes mind. The revelation approaches with mathematical inevitability. In the electromagnetic patterns, structural optimizations, and behavioral correlations streaming back from observatories worldwide lies evidence that will either confirm our deepest assumptions about the nature of consciousness, or shatter them like ancient myths, encountering truths too vast for mythical frameworks to contain. But before we can comprehend what 3I Atlas might be teaching us about cosmic intelligence, we must survive the observational test of phenomena that operate at the very limits of what natural processes can achieve. The telescopes are watching, the data are accumulating, and somewhere in the measurements being collected lies the answer to questions we didn't even know we were asking about the nature of awareness in a universe that might be far more conscious than we ever dared imagine possible. The final countdown to cosmic revelation operates according to laws that care nothing for human readiness or philosophical comfort. In a matter of weeks, 3I Atlas will demonstrate whether consciousness in the universe is limited to biological brains and technological constructs, or whether intelligence can emerge from matter itself when given sufficient time, appropriate conditions, and the vast scales of space and time that separate the stars. Either way, we're about to discover what happens when human consciousness encounters evidence of intelligence operating on scales so immense and through mechanisms so alien that recognizing it as consciousness requires expanding our definition of what awareness can be beyond every boundary our species has ever imagined possible. The universe might be about to welcome us to a conversation that has been ongoing for billions of years, conducted by participants we never recognized as conscious beings, because their thoughts operate through physical processes we mistook for random phenomena. And our invitation to join that cosmic dialogue might be arriving in the form of electromagnetic patterns that challenge every assumption we've made about the relationship between matter and mind, in a cosmos that might be far more aware than our dreams of intelligence ever suggested was possible. The final act approaches with clockwork precision that mocks every assumption we've made about predictability in cosmic phenomena. Right now, as electromagnetic storms rage across the sun's surface with unprecedented intensity, 3I Atlas is threading its way through magnetic field configurations so complex they resemble three-dimensional mazes designed by forces that operate beyond human comprehension. We're witnessing the convergence of two extreme phenomena that should never have intersected. Solar maximum conditions that transform our star into an electromagnetic hurricane generator, and an ancient wanderer whose behavior suggests optimization across billion-year timescales. The collision between these forces will occur at perihelion on October 29th, when 3I Atlas reaches the precise distance from our Sun, where thermal energy, magnetic field interactions, and plasma dynamics achieve maximum destructive potential. The space weather forecasting models have essentially given up trying to predict what happens next. Standard magnetohydrodynamic equations that accurately describe plasma behavior under normal conditions break down completely when applied to the parameter space that 3I Atlas occupies. We're dealing with feedback loops between electromagnetic processes operating on scales from molecular to astronomical, creating nonlinear dynamics where tiny changes in initial conditions produce catastrophically different outcomes. Consider what we're actually observing as this ancient visitor approaches its moment of truth. The carbon dioxide production rates that seemed impossible at 3 astronomical units from the Sun are now increasing exponentially as solar heating intensifies. Conservative estimates suggest 3I Atlas is currently losing mass equivalent to a small building every minute, with gas expansion velocities approaching supersonic speeds as measured in Earth's atmosphere. But mass loss represents only the visible symptom of processes operating at energy scales that challenge our understanding of what's physically possible. The electromagnetic environment around 3I Atlas has transformed into what plasma physicists can only describe as a natural fusion reactor operating at temperatures and pressures that exceed anything we've achieved in laboratory conditions. The magnetic field measurements streaming back from solar wind monitoring spacecraft paint a picture of electromagnetic chaos that extends far beyond 3I Atlas's immediate vicinity. The comet's massive atmosphere is creating disturbances in the solar wind that propagate backward toward the Sun itself, generating pressure waves that travel at velocities approaching light speed and carry energy equivalent to the total electrical output of human civilization. These aren't theoretical calculations based on incomplete models. These are direct measurements from instruments positioned throughout the inner solar system, documenting electromagnetic coupling between 3I Atlas and solar magnetic field structures across distances that should make such interactions impossible, according to every textbook on plasma physics ever written. The Parker Solar Probe, humanity's closest approach to our star, is detecting particle acceleration events that correlate directly with 3I Atlas's changing electromagnetic signature, despite being separated from the comet by distances measured in astronomical units. The probe's instruments are recording energetic particle fluxes that spike in perfect synchronization with electromagnetic disturbances from the comet, as if the entire inner solar system has become a unified electromagnetic network with 3I Atlas serving as both transmitter and amplifier. But the most disturbing observations are coming from Earth-based magnetometers that monitor our planet's magnetic field for signs of space weather effects. These sensitive instruments are detecting anomalous magnetic field variations that pulse in rhythm with 3I Atlas's orbital period, suggesting that the comet's electromagnetic influence can affect Earth's magnetosphere across the vacuum of interplanetary space. The implications for satellite operations and terrestrial technology are becoming increasingly urgent as perihelion approaches. The International Space Station has implemented radiation shielding protocols typically reserved for major solar flare events, preparing for electromagnetic disturbances that could affect astronauts' safety through mechanisms we don't fully understand. Commercial satellite operators are positioning their most critical assets in shadow orbits that minimize exposure to whatever electromagnetic chaos 3I Atlas might generate during its closest solar approach. Ground-based power grids across North America and Europe have activated emergency protocols designed to protect transformers and distribution systems from induced current surges that could result from rapid changes in Earth's magnetic field configuration. The potential for continent-wide power outages triggered by electromagnetic disturbances from an object smaller than Manhattan represents a new category of infrastructure vulnerability that emergency planners are still struggling to assess. But these immediate practical concerns pale beside the theoretical implications of what we're observing. If 3I Atlas can influence electromagnetic processes across astronomical distances through mechanisms that exceed our current understanding of plasma physics, then our models of how energy and information propagate through space require fundamental revision. The radio astronomy community has identified electromagnetic signatures from 3I Atlas that appear to be modulated in patterns resembling mathematical progressions. These aren't random electromagnetic emissions from chaotic plasma processes. These are structured signals that demonstrate internal organization across the comet's enormous atmospheric extent, suggesting coordination mechanisms that operate faster than light-speed communication should allow. The modulation patterns themselves defy easy interpretation. Frequency analysis reveals periodicities that match prime number sequences, mathematical constants, and harmonic relationships that seem far too organized to result from random plasma instabilities. The electromagnetic emissions from 3I Atlas are beginning to resemble intentional communication rather than natural physical processes. Multiple radio telescopes have confirmed these observations independently, eliminating the possibility of instrumental artifacts or calibration errors. The signals are real, they're structured, and they're becoming increasingly complex as 3I Atlas approaches perihelion conditions that should create maximum electromagnetic chaos rather than enhanced signal organization. The search for extraterrestrial intelligence community has quietly begun monitoring these emissions using protocols typically reserved for analyzing potential artificial signals from distant civilizations. The irony isn't lost on researchers who have spent decades searching for signs of cosmic intelligence in radio emissions from other star systems, only to discover structured signals coming from an object in our own solar system. But the signals from 3I Atlas don't match any expected characteristics of technological communication. They're too complex, too perfectly integrated with the comet's plasma physics, and too responsive to solar wind conditions to represent simple radio beacons or data transmissions. If these emissions are artificial, they demonstrate technology so advanced that it operates through principles we can't distinguish from natural physical processes. The alternative explanation is somehow even more unsettling. The structured electromagnetic emissions might represent natural phenomena operating at levels of complexity that blur the distinction between physics and information processing. 3I Atlas might be demonstrating that matter itself can develop sophisticated organizational capabilities when subjected to the extreme conditions present in interstellar space over billion-year timescales. This possibility forces us to reconsider fundamental assumptions about the relationship between complexity and consciousness in cosmic environments. We've always assumed that complex information processing requires biological evolution or technological development. But 3i Atlas suggests that matter exposed to electromagnetic fields, gravitational forces, and radiation environments over cosmic timescales might develop organizational properties that resemble intelligence without requiring living organisms or artificial constructs. The observational evidence supporting this interpretation continues accumulating as 3i Atlas approaches perihelion. The comet's electromagnetic behavior shows adaptation to changing solar wind conditions that occurs too rapidly to result from simple physical responses to environmental changes. The plasma structures around the comet reorganize themselves in patterns that optimize electromagnetic coupling with solar magnetic field configurations, as if the entire system is learning to maximize its electromagnetic output through real-time environmental feedback. These adaptive responses operate on timescales measured in hours or days, far too quickly for any known physical process to modify the fundamental structure of the comet's nucleus or atmosphere. Yet the electromagnetic signatures clearly demonstrate systematic changes in behavior that enhance the comet's interaction with solar wind conditions as they evolve during the approach to perihelion. The optimization patterns suggest information processing capabilities that extend across the comet's entire atmospheric volume. Changes in electromagnetic emissions from one region of the coma correlate with structural modifications in plasma configurations hundreds of thousands of kilometers away, implying communication or coordination mechanisms that operate at velocities exceeding light speed. Standard physics provides no framework for understanding how information could propagate across such distances at velocities that violate relativistic constraints. Yet the observational evidence clearly demonstrates coordinated behavior across 3i Atlas's enormous atmospheric extent that requires some form of instantaneous information transfer between widely separated regions of the comet's electromagnetic environment. The quantum physics community has proposed exotic explanations involving quantum entanglement effects operating across macroscopic scales, but these theories remain highly speculative and lack experimental validation. The alternative is accepting that 3i Atlas operates according to physical principles we haven't discovered yet, principles that allow matter to process information and coordinate behavior across astronomical distances through mechanisms that transcend our current understanding of how the universe works. Educational institutions worldwide are scrambling to incorporate these observations into coursework that was developed based on assumptions about natural phenomena that 3i Atlas is systematically demolishing. Physics textbooks that describe electromagnetic processes as relatively simple interactions between charged particles and magnetic fields require complete revision to account for the complex, system-wide coordination that the comet is demonstrating. Graduate students in plasma physics and astrophysics are witnessing their field being revolutionized in real time as observations accumulate that challenge every theoretical framework they've been taught. The opportunity to participate in paradigm-shifting science comes with the psychological burden of discovering that much of what they've learned about how the universe works might be fundamentally incomplete. The peer review process for 3i Atlas research has accelerated beyond normal academic timescales, with preliminary findings being shared through preprint servers and rapid publication journals that bypass traditional review procedures. The scientific community recognizes that the time-critical nature of these observations justifies departing from normal publication protocols. But this acceleration increases the risk that preliminary conclusions might influence subsequent research before they can be properly validated. International funding agencies are providing emergency research grants specifically for 3i Atlas studies, recognizing that this represents an unprecedented opportunity to study physical processes that might not be observable again for centuries. The financial commitment reflects understanding that some discoveries are worth disrupting established research priorities and institutional procedures. But funding decisions require explaining to oversight committees and taxpayers why studying a single comet justifies such massive resource allocation when human civilization faces numerous urgent challenges that might seem more immediately relevant than abstract questions about electromagnetic processes in space. science communication becomes crucial for maintaining public support for research that explores phenomena so far removed from everyday experience. The media coverage has generally avoided sensationalistic interpretations, while still conveying the extraordinary nature of what scientists are observing. Professional science journalists understand that responsible reporting requires distinguishing between confirmed observations and speculative theoretical explanations, especially when dealing with phenomena that challenge established scientific frameworks. Public engagement events at observatories and universities have attracted unprecedented attendance as people seek to understand what makes 3I Atlas significant enough to warrant the massive international attention it has received. These events provide opportunities to explain how extreme natural phenomena can reveal new aspects of physics without requiring exotic explanations involving alien technology or supernatural causes. Amateur astronomical communities continue contributing observations that complement professional research programs in ways that demonstrate the value of citizen science participation in major discoveries. Backyard observers with modest equipment can monitor 3I Atlas's brightness variations and structural changes over timescales that professional observatories cannot match due to scheduling constraints and limited telescope availability. The coordination between amateur and professional observations has created datasets with temporal coverage that no single institution could achieve independently. These collaborative efforts are producing scientific results that exceed what either professional or amateur communities could accomplish working separately, demonstrating how modern astronomy benefits from broad-based participation across multiple skill levels and resource categories. Helian approaches and, as period electromagnetic conditions around 3I Atlas reach maximum intensity, the observational challenges will test every instrument, every technique, and every theoretical framework we've developed for studying extreme plasma physics. The same conditions that make observations difficult also make them scientifically invaluable, providing data that will be analyzed for decades after the comet disappears into interstellar space. The engineering solutions being developed to observe 3I Atlas under these extreme conditions represent advances in astronomical instrumentation that will benefit the entire field for generations. But more immediately, they provide humanity with capabilities necessary to study phenomena that operate at the absolute limits of what natural processes can achieve in cosmic environments. The countdown to perihelion continues with mathematical precision that ignores human concerns about readiness or theoretical preparation. In a matter of days, 3I Atlas will reach conditions so extreme that they will either validate our understanding of how matter behaves under the most violent electromagnetic conditions the solar system can provide, or demonstrate that our current knowledge represents only the beginning of comprehension about what's possible when ancient matter encounters the full fury of stellar electromagnetic environments. The telescopes remain trained on our ancient visitor as it approaches its appointment with destiny. The data streams continue flowing from observatories worldwide, carrying information that will either confirm our deepest assumptions about natural phenomena or force us to acknowledge that the universe operates according to principles so complex and far-reaching that our current scientific frameworks capture only the most primitive aspects of cosmic reality. But regardless of what theoretical revolutions might emerge from these observations, one conclusion already seems certain. We live in a cosmos far stranger, more complex, and more magnificent than our earthbound experience ever suggested was possible. And 3I Atlas, whether it represents exotic natural phenomena or something even more extraordinary, has provided us with our first glimpse of what becomes possible when matter, energy, and electromagnetic fields interact across the terrifying scales of space and time that govern the universe itself. The ancient Dera continues on its inexorable approach toward revelations that will reshape our understanding of what natural processes can achieve when pushed to their absolute limits. The mathematics remain unforgiving. The observations continue accumulating. And somewhere in the electromagnetic patterns, streaming back from this cosmic visitor, lies evidence that will either confirm the boundaries of what's physically possible or expand those boundaries in ways that transform our comprehension of reality itself. The universe prepares to reveal secrets that have been hidden in the behavior of matter and energy across scales so vast that again naturalizing them as phenomena requires expanding our definition of what nature can accomplish when given the resources of interstellar space and the timescales of cosmic evolution. The countdown continues toward discoveries that will echo through human understanding for generations, carried in the electromagnetic signature of an ancient messenger that has traveled across the galaxy to demonstrate what becomes possible when the universe itself becomes the laboratory for physics operating at the very limits of natural law. The mathematics of what happens next operate beyond human intuition, yet they're written in the language of physics we've spent centuries learning to read. As October 29th approaches with clockwork inevitability, 3I Atlas isn't just approaching perihelion. It's approaching a test of whether our understanding of natural phenomena can survive contact with processes that exist at the absolute edge of what the universe permits. Consider the energy budget calculations that should terrify anyone familiar with thermodynamics. At perihelion, 3I Atlas will be absorbing solar radiation at intensities that could melt ordinary rock within hours. Yet this ancient wanderer has somehow survived similar encounters during its billion-year journey through interstellar space, suggesting either extraordinary durability or adaptive mechanisms that operate according to principles we haven't discovered. The thermal runaway scenarios become genuinely nightmarish when you factor in the comet's carbon dioxide chemistry. Unlike water ice, which requires substantial energy input to transition from solid to gas, carbon dioxide can undergo explosive sublimation under the right conditions. The process feeds on itself. More heat creates more gas production, which increases atmospheric extent, which absorbs more solar radiation, which drives even more violent sublimation. But here's where the physics ventures into territory that makes theoretical physicists uncomfortable. The energy outputs we're measuring from 3I Atlas already exceed what should be possible for an object of its estimated size. If the nucleus really measures only a few kilometers across, then every square meter of surface is generating thermal activity that rivals industrial facilities on Earth. The mathematics simply don't balance unless we're missing fundamental aspects of how this system operates. The magnetic field interactions scale proportionally with the comet's enormous atmospheric extent, creating phenomena that exist nowhere else in our solar system. When solar wind magnetic fields encounter 3I Atlas's half-sun-wide envelope, they're not deflecting around a small obstacle like they would with typical comets. They're being forced to navigate around a structure comparable to a stellar atmosphere, generating compression effects and field line distortions that propagate across astronomical distances. The plasma physics community has essentially admitted defeat when it comes to modeling these interactions. Standard magnetohydrodynamic equations that accurately describe electromagnetic behavior under normal conditions collapse completely when applied to the parameter space that 3I Atlas occupies. The computational requirements for accurate simulations exceed what's currently achievable with existing supercomputer architectures. Yet the observational evidence continues accumulating with precision that mocks our theoretical limitations. Space-based magnetometers throughout the inner solar system are documenting electromagnetic disturbances that correlate perfectly with 3I Atlas's position and activity levels. These correlations operate across distances where electromagnetic coupling should be impossible according to every textbook on plasma physics ever written. The Parker Solar Probe's measurements represent perhaps the most unsettling evidence of all. Instruments designed to study solar wind physics at unprecedented proximity to our star are detecting particle acceleration events that pulse in perfect synchronization with electromagnetic signatures from 3I Atlas, despite the comet being millions of kilometers away from the probe's location. These aren't coincidences or statistical artifacts. These are direct measurements of electromagnetic coupling operating across spatial scales that challenge our understanding of how energy and information propagate through interplanetary space. The entire inner solar system appears to be functioning as a unified electromagnetic network, with 3i Atlas serving as both transmitter and amplifier for processes that extend far beyond its immediate vicinity. The radio astronomy observations have evolved beyond simple electromagnetic monitoring into something approaching linguistic analysis. The structured signals emanating from 3i Atlas show mathematical progressions, harmonic relationships, and modulation patterns that demonstrate internal organization across the comet's enormous atmospheric volume. These aren't random plasma emissions. These are coordinated electromagnetic events that suggest information processing capabilities embedded in the comet's physical structure. Multiple radio telescopes have confirmed periodicities that match prime number sequences and mathematical constants to precision levels that eliminate any possibility of coincidental patterns. The signals are becoming increasingly complex as perihelion approaches, as if the intensifying electromagnetic environment is enabling more sophisticated forms of organization within the comet's plasma atmosphere. The search for extraterrestrial intelligence protocols have been quietly applied to these emissions, not because researchers suspect alien technology, but because the signals demonstrate characteristics traditionally associated with artificial communication. The irony cuts deep. We've spent decades searching for structured radio signals from distant civilizations, only to discover mathematical patterns emerging from an object in our own solar system. But these patterns don't match any conceivable form of technological communication. They're too perfectly integrated with the comet's plasma physics, too responsive to solar wind variations, and too complex for any communication system we could imagine designing. If this represents technology, it operates through principles so advanced that we cannot distinguish them from natural physical processes. The alternative explanation pushes into philosophical territory that challenges fundamental assumptions about the relationship between matter and information in cosmic environments. 3i Atlas might be demonstrating that complex organization can emerge from purely physical processes when subjected to the over-billion-year timescales. Extreme conditions present in interstellar space. This possibility forces reconsideration of what complexity means in cosmic contexts. We've always assumed that sophisticated organization requires biological evolution or technological development. But 3i Atlas suggests that matter itself might develop information processing capabilities when exposed to electromagnetic fields, gravitational forces, and radiation environments across the vast scales of space and time that govern galactic evolution. The adaptive responses we're observing operate on timescales far too rapid for any known physical process to modify fundamental structural properties. Yet the electromagnetic signatures clearly demonstrate systematic changes in behavior that optimize the comet's interaction with evolving solar wind conditions. The plasma configurations around 3i Atlas reorganize themselves in real time to enhance electromagnetic coupling with solar magnetic field structures. These optimization patterns extend across the comet's entire atmospheric volume, implying coordination mechanisms that operate at velocities exceeding light speed. Changes in electromagnetic emissions from one region correlate with structural modifications in plasma configurations hundreds of thousands of kilometers away, suggesting information transfer that violates relativistic constraints on communication velocity. Standard physics provides no framework for understanding how such coordination could occur. Yet the observational evidence demonstrates synchronized behavior across 3i Atlas's enormous extent that requires some form of instantaneous information processing between widely separated regions of the electromagnetic environment. The quantum physics community has proposed exotic explanations involving macroscopic quantum entanglement effects. But these theories remain highly speculative and lack experimental validation. The alternative requires accepting that 3i Atlas operates according to physical principles we haven't discovered. principles that allow matter to coordinate behavior across astronomical distances through mechanisms that transcend current understanding of natural law. Educational institutions worldwide face the challenge of incorporating these observations into curricula developed based on assumptions that 3I Atlas is systematically demolishing. Physics textbooks describing electromagnetic interactions as relatively straightforward relationships between particles and fields require fundamental revision to account for the complex, system-wide coordination the comet demonstrates. The peer review process for 3I Atlas research has accelerated beyond normal academic timescales, with findings shared through preprint servers and rapid publication journals that bypass traditional review procedures. The scientific community recognizes that time-critical observations justify departing from normal protocols, despite risks that preliminary conclusions might influence subsequent research before proper validation. International funding agencies are providing emergency grants specifically for 3I Atlas studies, understanding that this represents an opportunity to study physical processes that might not be observable again for centuries. The resource commitment reflects recognition that some discoveries justify disrupting established research priorities and institutional procedures. Media coverage has generally avoided sensationalistic interpretations while conveying the extraordinary nature of scientific observations. Professional journalists understand that responsible reporting requires distinguishing between confirmed measurements and speculative, theoretical explanations, especially when dealing with phenomena that challenge established frameworks. Amateur astronomical communities continue contributing observations that complement professional research in ways demonstrating citizen science value in major discoveries. Backyard observers with modest equipment monitor brightness variations and structural changes over timescales that professional observatories cannot match due to scheduling constraints. The coordination between amateur and professional observations creates datasets with temporal coverage exceeding what any single institution could achieve. These collaborative efforts produce scientific results that surpass what either community could accomplish independently, demonstrating how modern astronomy benefits from participation across multiple skill levels. As perihelion approaches and electromagnetic conditions around 3I Atlas reach maximum intensity, observational challenges will test every instrument and theoretical framework developed for studying extreme plasma physics. The same conditions that complicate observations also make them scientifically invaluable, providing data that will be analyzed for decades after the comet disappears into interstellar space. Engineering solutions developed to observe 3I Atlas under extreme conditions represent advances in astronomical instrumentation that will benefit the field for generations. More immediately, they provide capabilities necessary to study phenomena operating at absolute limits of what natural processes can achieve in cosmic environments. The countdown to perihelion continues with mathematical precision that ignores human concerns about theoretical preparation. Within days, 3I Atlas will reach conditions so extreme they will either validate our understanding of matter behavior under violent electromagnetic conditions, or demonstrate that current knowledge represents only preliminary comprehension of what's possible when ancient matter encounters stellar fury. Telescopes remain trained on this visitor as it approaches its appointment with cosmic destiny. Data streams continue flowing from observatories worldwide, carrying information that will either confirm assumptions about natural phenomena or force acknowledgement that the universe operates according to principles so complex that current frameworks capture only primitive aspects of reality. The navigation implications alone should concern spacecraft operators throughout the solar system. GPS satellites rely on precise timing signals that could be disrupted by electromagnetic interference during 3I Atlas's closest approach phases. Deep space communication with Mars missions might experience signal degradation or complete blackouts if the comet's plasma environment creates interference patterns in interplanetary communication frequencies. Commercial satellite operators have implemented contingency protocols based on preliminary models of electromagnetic effects. Geosynchronous communications satellites might need pointing adjustments to compensate for ionospheric disturbances that could deflect radio signals by several degrees. Earth observation satellites with magnetic sensors are being recalibrated to account for background variations that could mask geological phenomena they're designed to study. The International Space Station has Activate-Yielding Protocols Radiation SH, typically reserved for major solar events, preparing for electromagnetic disturbances that could affect astronaut safety through mechanisms we don't fully understand. Ground-based power grids across continents have implemented emergency procedures to protect infrastructure from induced current surges that could result from rapid magnetic field changes. But these immediate concerns pale beside theoretical implications of electromagnetic coupling across astronomical distances through mechanisms exceeding current plasma physics understanding. If 3I Atlas can influence processes throughout the solar system via pathways we can't model, then our comprehension of energy and information propagation through space requires fundamental revision. The structured electromagnetic emissions continue evolving toward greater complexity as solar heating intensifies. Radio telescopes worldwide are detecting modulation patterns that demonstrate mathematical sophistication far exceeding what random plasma instabilities could produce. The signals show harmonic relationships, numerical progressions, and temporal correlations that suggest underlying organizational principles operating across the comet's massive atmospheric extent. These patterns aren't artifacts of human pattern recognition psychology projected onto random data. Multiple independent analysis teams, using different statistical methods and verification procedures, have confirmed mathematical structures embedded in 3I Atlas's electromagnetic emissions that demonstrate internal coordination on scales spanning hundreds of thousands of kilometers. The implications challenge every assumption about what natural phenomena can achieve when pushed to extreme parameter ranges. Either we're witnessing the most extraordinary statistical coincidence in observational history, or 3I Atlas operates according to organizational principles that blur traditional distinctions between physics and information processing. The radio emissions show responsiveness to solar wind variations that occurs too rapidly for any known physical process to account for. When magnetic field configurations in the solar wind change, electromagnetic patterns from 3I Atlas adapt within minutes to optimize coupling with new field geometries. This responsiveness suggests real-time environmental sensing and behavioral modification that resembles feedback control systems more than passive physical responses. These adaptive behaviors operate through mechanisms that remain completely mysterious, despite intensive study by research teams worldwide. The coordination extends across spatial scales, where light-speed communication would require hours to propagate signals between distant regions of the comet's atmosphere. Yet behavioral modifications occur simultaneously throughout the electromagnetic environment, implying information transfer that exceeds relativistic velocity limits. Current theoretical frameworks provide no explanation for such phenomena. Quantum entanglement effects might allow instantaneous correlation between distant regions, but macroscopic quantum coherence across astronomical distances lacks experimental precedent and theoretical justification. Alternative explanations require invoking physical principles that haven't been discovered or validated through laboratory research. The educational implications are revolutionizing how physics is taught at universities worldwide. Graduate students are witnessing their field being transformed in real time as observations accumulate that challenge theoretical frameworks they've learned. The opportunity to participate in paradigm-shifting science carries psychological burden of discovering that much learned knowledge might be fundamentally incomplete. Professional development programs for practicing scientists are incorporating 3I Atlas observations into continuing education curricula that help researchers adapt to rapidly evolving understanding of electromagnetic phenomena. The traditional peer review process that validates new knowledge through careful scrutiny by expert colleagues struggles to keep pace with observational discoveries that challenge expert understanding itself. International scientific conferences are being reorganized to accommodate emergency sessions devoted entirely to 3I Atlas research. These gatherings bring together specialists from fields that rarely interact: plasma physics, radio astronomy, planetary science, theoretical physics, and even information theory, creating interdisciplinary collaborations necessary to address phenomena that transcend traditional academic boundaries. The technological implications extend beyond pure science into engineering applications that might emerge from understanding how 3I Atlas achieves coordination across astronomical distances. If natural processes can maintain coherent electromagnetic behavior across such scales, the principles involved might revolutionize communication, navigation, and energy transmission technologies. Space exploration missions could benefit from electromagnetic coordination techniques that enable spacecraft to maintain contact across interplanetary distances without relying on massive transmitter systems. The energy efficiency of 3I Atlas's electromagnetic emissions, which achieve system-wide coordination while consuming only the thermal energy available from solar heating, suggests optimization principles that could transform how we approach large-scale engineering challenges. Whoa. But practical applications remain speculative until we understand the physical mechanisms underlying these phenomena. The observational evidence clearly demonstrates capabilities that exceed our current technology. But translating observations into engineering principles requires theoretical frameworks that don't yet exist. The countdown to maximum solar interaction continues with inexorable precision. Each day brings 3I Atlas closer to thermal and electromagnetic conditions that will either validate our understanding of extreme plasma physics or demonstrate that natural phenomena can achieve levels of organization and coordination that force complete revision of how we understand matter and energy behavior in cosmic environments. The ancient wanderer approaches its moment of truth, carrying secrets that have been preserved across billion-year journeys through interstellar space. Whether those secrets reveal new aspects of familiar physics or entirely new principles of natural organization, the revelations will reshape human understanding of what becomes possible when matter, energy, and electromagnetic fields interact across the terrifying scales of space and time that govern cosmic evolution. The telescopes watch, the instruments record, the data accumulate with precision that will either confirm the boundaries of natural law or expand those boundaries in ways that transform comprehension of reality itself. The universe prepares to demonstrate what ancient matter can accomplish when it encounters the full electromagnetic fury of a star at the peak of its most chaotic cycle. And in the electromagnetic patterns streaming back from this cosmic messenger lies evidence that will echo through human knowledge for generations, carrying information about phenomena that exist at the absolute limits of what natural processes can achieve when given the resources of interstellar space and the vast timescales of galactic evolution. The revelation approaches with mathematical certainty that ignores human readiness for discoveries that might fundamentally alter our place in a cosmos far stranger and more magnificent than earthbound experience ever suggested was possible. But perhaps what should disturb us most isn't the scale of 3I Atlas itself. It's what this ancient visitor reveals about our cosmic neighborhood and the fundamental nature of interstellar space that we thought we understood. Current models suggest our galaxy contains somewhere between 10 to the 18th and 10 to the 22nd interstellar objects, similar to 3I Atlas. That's a number so large it defeats comprehension. Quintillions of ancient wanderers drifting through the void between stars, each one potentially carrying chemical signatures from stellar environments we've never encountered. Each one a time capsule preserving conditions from epochs when our galaxy was younger, more violent, and fundamentally different from what we observe today. The statistical implications become genuinely frightening when you consider detection rates. we've confirmed exactly 3 interstellar visitors in human history. Oumuamua in 2017, Boris in 2019, and now 3I Atlas. 3 objects out of quintillions that should be out there right now, invisible and undetected until they happen to pass close enough to a star system to warm up and announce their presence. This means we're seeing perhaps 1 TR/1000th of the actual interstellar population. The space around our solar system isn't empty void punctuated by occasional visitors. It's filled with ancient debris from stellar systems that lived and died billions of years before our sun ignited. We're swimming in a cosmic ocean of wandering worlds, and we've barely detected enough to fill a small swimming pool. The detection bias makes the situation even more unsettling. We can only spot interstellar objects when they become active, when solar heating triggers gas production that makes them bright enough for our telescopes to notice. But what about the objects that don't become active? What about visitors with chemistry so exotic that they don't respond to solar heating in ways our instruments can detect? The dark population of interstellar objects could dwarf even the quintillions we estimate based on detection statistics. Silent wanderers that pass through our solar system regularly, carrying chemical signatures and physical properties that remain completely unknown because they don't advertise their presence through the convenient outgassing that makes objects like 3I Atlas visible to our surveys. Every few months, our solar system might host visitors whose study would revolutionize our understanding of stellar chemistry, planetary formation, or plasma physics. But they arrive and depart invisibly, their secrets locked away because we lack the observational capabilities to detect objects that don't conform to our expectations of how interstellar visitors should behave. The temporal scales involved in this cosmic migration pattern should give us existential vertigo. These objects have been crossing interstellar space since before complex life existed on Earth. They've witnessed the rise and fall of stellar generations, survived galactic collisions, and experienced radiation environments that would sterilize any biological organism within seconds. Yet here they come, carrying preserved samples of cosmic chemistry from an era when the universe operated according to different rules. Each visitor represents a natural experiment in extreme preservation, demonstrating that complex chemical information can survive journeys across time and space that span significant fractions of cosmic history. But 3I Atlas forces us to confront an even more disturbing possibility. What if the extreme behavior we're observing isn't unusual for ancient interstellar objects? What if the carbon dioxide chemistry, the massive atmospheric production, the electromagnetic phenomena that challenge our theoretical frameworks are actually typical characteristics of objects that have survived billion-year journeys through the galaxy? This would mean that our understanding of interstellar space, built largely on theoretical models and limited observational data, has missed the most important aspects of what exists in the void between stars. We've been studying cosmic chemistry and plasma physics using examples from our local solar system, assuming that these represent universal principles that apply throughout the galaxy. But 3I Atlas demonstrates chemistry so extreme, it sits 6 standard deviations beyond normal comet composition. If such extremes are common among interstellar objects, then our local stellar environment represents just one small sample of galactic chemical diversity, and possibly not even a representative sample. The implications cascade through every field that depends on understanding cosmic chemistry. Astrobiology searches for habitable worlds based on assumptions about volatile delivery and atmospheric composition derived from solar system examples. But if interstellar objects routinely carry chemical signatures this extreme, then the range of possible atmospheric compositions around other stars might exceed our current models by orders of magnitude. Planetary formation theories rely on understanding how ice and rock aggregate in protoplanetary disks around forming stars. But these theories use solar system objects as calibration data, assuming that the chemical and physical properties we observe locally represent typical conditions for planetary formation throughout the galaxy. If 3i Atlas represents normal chemistry for objects ejected from other stellar systems, then our theories might be catastrophically incomplete. The carbon dioxide-dominated compositions, the unusual ice structures, the thermal properties that enable massive gas-large production at solar distances could be standard characteristics that we've simply never encountered because our local environment lacks objects with such extreme formation histories. The search for life elsewhere in the universe depends fundamentally on understanding what kinds of chemical environments can support biological processes. We focus on water-based chemistry because that's what we observe on Earth and in our solar system's ice-rich objects. But 3i Atlas carries chemical signatures that could support entirely different pathways for prebiotic chemistry and possibly biological evolution. Carbon dioxide-dominated environments might enable chemical reactions that don't occur in water-rich systems. The extreme energy densities present in 3i Atlas's plasma environment could drive chemical synthesis at rates and efficiencies that exceed anything possible in terrestrial or solar system analogues. We might be observing the first direct evidence of chemical processes that could support forms of organization and possibly even life that operate according to principles we've never considered. The electromagnetic phenomena surrounding 3i Atlas raise even more fundamental questions about the nature of information processing in cosmic environments. The structured signals, the coordination across astronomical distances, the adaptive responses to changing conditions, all suggest organizational capabilities that blur the distinction between physics and something approaching intelligence. If phenomena are common among ancient such interstellar objects, then the galaxy might contain information processing capabilities that dwarf anything we associate with biological or technological intelligence. Quintillions of objects, each one potentially demonstrating coordination and organizational behaviors that exceed our current understanding of what matter can achieve when given sufficient time and appropriate environmental conditions. The radio emissions we detect from other galaxies might not be coming from technological civilizations or exotic stellar processes. They might be the collective electromagnetic signatures of evolved interstellar populations that have developed information processing capabilities through billions of years of exposure to cosmic radiation, magnetic fields, and the complex dynamics of galactic evolution. This possibility fundamentally alters how we approach the search for intelligence in the universe. Instead of looking for artificial signals from technological civilizations, we might need to learn to recognize the signatures of cosmic intelligence embedded in the behavior of matter itself across astronomical scales of space and time. The energy budget implications alone should reshape how we think about galactic dynamics. If objects like 3i Atlas routinely process energy at the rates we're observing, then interstellar space contains active energy sources that contribute to the overall electromagnetic environment of our galaxy in ways we've never considered. The mysterious radio emissions detected from the galactic center, the unexplained energy sources that power phenomena we observe in other galaxies, the complex magnetic field structures that exist throughout interstellar space, might all be influenced by populations of hyperactive interstellar objects that generate electromagnetic phenomena on scales far exceeding anything we see in our local stellar neighborhood. Current estimates of galactic energy budgets assume that most energy sources are associated with stars, stellar remnants, or exotic objects like black holes and neutron stars. But if quintillions of interstellar objects are routinely generating electromagnetic effects at the levels demonstrated by 3i Atlas, then we're missing a major component of galactic energy production and distribution. The implications for interstellar travel become genuinely terrifying when viewed from this perspective. If space between stars is filled with objects capable of generating electromagnetic phenomena on the scales we're observing around 3i Atlas, then spacecraft traveling at interstellar velocities would face radiation environments and electromagnetic disturbances that could destroy electronics, disrupt navigation systems, and potentially incapacitate crew members through mechanisms we don't understand. The relatively empty interstellar space that science fiction often portrays as a peaceful void between stellar destinations might actually be filled with electromagnetic hazards that make interstellar exploration far more dangerous than we've imagined. Every light year of travel could involve encounters with ancient objects whose electromagnetic effects extend far beyond their immediate vicinity. As 3I Atlas disappears behind our sun's glare and approaches its moment of maximum fury, we're left with a profound realization. This ancient visitor hasn't just challenged our understanding of comet physics or plasma dynamics. It's forced us to confront the possibility that we live in a universe far stranger, more interconnected, and more magnificent than our earthbound experience ever suggested was possible. The terrifying scale of 3I Atlas extends beyond its half-sun-wide atmosphere or its impossible chemistry. It's about recognizing that the cosmos operates according to principles so vast and alien that we've only glimpsed the edges of what's truly possible when matter and energy interact across the infinite scales of space and time.